Sekali lagi kami ucapkan terima kasih, selamat datang dalam acara seminar Rekayasa Kegempaan 2023. Kami persilahkan Bapak Ibu yang sudah hadir di ruangan acara, kami persilahkan untuk langsung menempati tempat duduk yang sudah kami sediakan. Ladies and gentlemen, we cordially invite you to gather at this venue because in a few minutes we will start this event of the Earthquake Engineering Seminar. Thank you. Oke, selamat pagi. Kami ingatkan sekali lagi untuk Bapak Ibu yang sudah hadir di ruangan acara, kami persilakan untuk langsung menempati tempat duduk yang sudah kami sediakan. 1 menit lagi acara akan kami mulai. Sekali lagi kami ingatkan untuk Bapak-Bapak, Ibu-Ibu yang sudah hadir di ruangan acara, kami persilakan untuk langsung menempati tempat duduk yang sudah kami sediakan. Ladies and gentlemen, we cordially invite you to gather in this venue because in a few minutes we will start this event of earthquake engineering seminar. Thank you. Oke, Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi semuanya. Kita mau cek dulu, ini tadi sudah coffee morning, tapi kok nampaknya ini belum seperti coffee morning. Kita boleh cek dulu ya. Selamat pagi semuanya. Ini skala 1 sampai 10 ya, kalau boleh saya skalakan mungkin ini hanya 2 ya. Kita boleh bakar semangatnya lagi pagi hari ini. Selamat pagi semuanya. Mantap, itu 1 sampai 10 saya kasih skor 20. Luar biasa, boleh tepuk tangan untuk kita semuanya. Selamat pagi semuanya, selamat datang di acara Seminar Rekayasa Kegempaan 2023 yang akan membahas mengenai tantangan Insinyur terhadap perkembangan rekayasa kegempaan untuk minimalisasi kerugian kegagalan bangunan. Ini sebetulnya tema yang sangat menarik dan juga sampai saat ini masih menjadi diskursus karena kita tahu kondisi Indonesia ini merupakan negara yang rawan gempa, sehingga dengan adanya diskusi pada pagi hari ini kita bisa mengetahui seperti apa kesiapsiagaan kita menghadapi kondisi objektif dari Indonesia yang dikategorikan sebagai negara yang rawan bencana. Acara ini diselenggarakan oleh Badan Kejuruan Sipil Persatuan Insinyur Indonesia bersama dengan Kementerian PUPR dan didukung oleh Tamara Overseas Corporindo. Sekali lagi boleh kita minta tepuk tangannya untuk kita semuanya. Good morning, ladies and gentlemen. Welcome to the Earthquake Engineering Seminar at Ministry of Public Works and Public Housing to discuss about the engineers' challenge to development of earthquake engineering to minimize building failure loss. And this event was organized by the Civil Vocational of the Indonesian Engineers Association with the Ministry of Public Works and Public Housing, supported by Tamara Overseas Corporindo. Kami ucapkan terima kasih dan selamat datang kepada seluruh tamu undangan yang sudah hadir, baik yang hadir secara offline maupun online. Tadi saya lihat ini sudah banyak sekali yang hadir secara online, kurang lebih ada 900 ya ini ya. Tadi ya, kita boleh minta tepuk tangan sekali lagi, kita bakar semangatnya pagi hari ini. On behalf of the organizers, we would like to extend a warm welcome and express our gratitude to all the guests that coming for this event. It's an honor for me to welcome all of the honorable guests. Bapak Endra S. Atmawijaya selaku staf ahli Menteri PU, terima kasih sudah berkenan untuk hadir. Kemudian Pak Kimron Manik, Direktur Keberlanjutan Konstruksi. Bapak Sutopo Kristanto, selaku Ketua Badan Kejuruan Sipil PI, terima kasih sudah hadir. Kemudian ada Pak Fahmi Aldimar, Kepala Balai Geoteknik, Terowongan dan Struktur PUPR. Kemudian Pak Elmiko Pangestu selaku Direktur Tamara Overseas Corporindo. Bapak Ibu pengurus Persatuan Insinyur Indonesia dan pengurus Badan Kejuruan Sipil PII. Serta tamu-tamu yang hadir wakil dari Badan Nasional Penanggulangan Bencana BNPB yang mewakili dan universitas di Jabotabek. Kita boleh minta tepuk tangan sekali lagi. Thank you so much for your coming for this event in this morning. Dan first of all, let me introduce myself. My name is Kinavita and I will be the master of ceremony for this special event. Perkenalkan, saya Ginavita yang akan memandu jalannya acara pada pagi hari ini. Untuk memulai acara, langsung saja kita masuk ke agenda yang pertama. Kita akan menyanyikan lagu kebangsaan Indonesia Raya. Untuk Bapak Ibu kami persilahkan untuk berdiri. The next agenda is sing the national anthem of Indonesia Raya. And for all of the ladies and gentlemen, please stand up. Hadirin dimohon untuk tetap berdiri karena selanjutnya kita akan menyanyikan lagu Himne Persatuan Insinyur Indonesia. Kami persilakan.
Kami Insinyur Indonesia berbudi luhur dan berintegritas, kompeten dan profesional, bertanggung jawab sepenuh hati. Kami Insinyur Indonesia, kami menerangi negeri, mempersatukan Nusantara, membuka cakrawala dunia. Kami Insinyur Indonesia, kami memajukan bangsa, mensejahterakan masyarakat untuk kemanusiaan semesta alam. Kami Insinyur Indonesia, siap membangun bangsa.
Untuk para hadirin kami persilakan duduk kembali. Ladies and gentlemen, please have a seat. Thank you. Selanjutnya, kita akan mendengarkan sambutan dari Ketua Badan Kejuruan Sipil PII, Bapak Sutopo Kristanto. Ladies and gentlemen, welcoming speech from Chairman of the Civil Vocational Agency, Mr. Sutopo Kristanto. Time is yours.
Bismillah. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sejahtera untuk kita semua. Salam, namo buddhaya, salam kebajikan. Yang kami hormati Bapak Staf Ahli Menteri PUPR Republik Indonesia, Bapak Endra Atmawijaya. Selamat pagi Bapak dan terima kasih atas kesempatan fasilitas ruangan yang telah diberikan kepada kami. Yang kami hormati Bapak-bapak pejabat di lingkungan Kementerian PUPR yang pada hari ini telah hadir bersama kami. Terima kasih atas kehadirannya. Di sini kami juga hadir bersama dengan tim PK Sipil PII. Dan tentunya pada kesempatan ini kami juga mengucapkan terima kasih kepada Ketua Umum Persatuan Insinyur Indonesia, Bapak Danis Sumadilaga, yang nantinya akan memberikan sambutan kepada kita semua sebagai mengantarkan untuk seminar kali ini, seminar yang dilaksanakan oleh PK Sipil yang terkait dengan kegempaan. Tentunya marilah kita pertama-tama memanjatkan puji syukur kehadirat Tuhan Yang Maha Kuasa atas nikmat dan rahmat-Nya bahwa pagi ini kita dapat menghadiri seminar pada hari ini. Dan pada kesempatan ini kami juga menyampaikan terima kasih kepada para pemateri yang pada hari ini juga telah hadir bersama kita, beberapa tokoh baik dari dalam maupun dari luar negeri yang nantinya akan di-announce oleh pembawa acara, moderator yang pada hari ini akan bersama-sama dengan kita. Sebagai laporan Bapak Staf Ahli bahwa seminar ini diikuti di samping oleh peserta offline adalah juga peserta online yang terdaftar di kami saat ini mencapai 900 orang. Jadi kita saat ini juga sudah sangat mudah untuk melakukan komunikasi, baik komunikasi yang bersifat teknis dan profesi. Oleh karena itu, saya mengucapkan terima kasih kepada para peserta dan juga para panelis yang hadir pada kesempatan hari ini. Yang kedua, bahwa seminar kegempaan ini kita laksanakan karena beberapa waktu yang lalu kita mengalami gempa yang terjadi di Cianjur. Gempa ini telah juga memberikan kesadaran kita sebagai salah satu insan profesi untuk memikirkan apakah peran profesi keinsinyuran terutama di sipil ini terhadap masalah-masalah yang terkait dengan kegempaan. Oleh karena itu, beberapa waktu setelah kejadian gempa di Cianjur itu, BK Sipil melakukan serangkaian pertemuan dengan tokoh ahli dan juga terlibat pada waktu penanganan gempa itu, Bapak. Jadi kami laporkan, kami juga bersama dengan Badan Nasional Penanggulangan Bencana, ini di samping melakukan verifikasi terhadap gempa dan juga mekanisme runtuh yang ada di Cianjur, tetapi juga membantu BNPB dan Pemda Jawa Barat dan juga Pemda Cianjur setempat untuk memberikan dukungan kepada masyarakat, terutama tentang verifikasi penyebab gempa dan efek terhadap gempa, sehingga proses-proses yang harus dilaksanakan pasca gempa itu telah berlangsung dengan baik dan cepat. Namun demikian, dari sisi bagaimana kita akan memberikan respon yang akurat terhadap gempa ini, kita pada hari ini sangat beruntung bahwa kita juga masih bisa diberikan kesempatan untuk melakukan interaksi dengan tokoh-tokoh kita, baik tokoh nasional maupun tokoh internasional yang terkait dengan bagaimana kita melakukan manajemen gempa ini. Jadi bersama kita pada hari ini telah hadir juga dua ahli dari luar negeri, dari MIT, ya, dan juga dari dalam negeri, jadi dari kita Pak Fahmi dan juga dari universitas, dari Profesor Bambang Suhendro, yang nanti akan bersama kita untuk melaksanakan kajian yang bersifat strategik. Artinya apa? Artinya adalah kita harus mampu memiliki antisipatif terhadap apa yang akan terjadi kepada kita jika gempa itu terjadi di Indonesia. Seperti kita ketahui bahwa gempa ini juga telah dilakukan penyesuaian terhadap respon kita terhadap standar atau kriteria desain. Arahan-arahan pemerintah melalui Kementerian PUPR juga sudah memberikan satu respon yang cukup baik, yaitu dengan mengharuskan kita pada beberapa tahun yang lalu itu untuk memberikan koreksi terhadap adanya faktor gempa yang harus diaplikasikan di dalam setiap perhitungan konstruksi. Namun pertanyaannya adalah, apakah fasilitas-fasilitas yang terjadi sebelum peraturan gempa ini berlaku itu, apakah fasilitas-fasilitas ini memiliki ketahanan terhadap kegempaan yang akan terjadi nantinya? Concern BK Sipil itu tentunya faktor ini terkait dengan juga lingkungan, yaitu apakah gempa ini akan mengakibatkan terjadi di kota-kota besar seperti Jakarta, Surabaya, Semarang, dan daerah utara yang diklasifikasikan menjadi daerah yang memiliki risiko kegempaan cukup tinggi. Oleh karena itu, Saya kira ada satu, yang kedua adalah next itu kita membangun sistem respon kegempaan yang cukup handal. Yang kedua bagaimana program retrofit terhadap bangunan-bangunan yang belum memenuhi standar Kementerian PUPR atau standar yang diterbitkan oleh pemerintah pada waktu hari ini. Kan banyak bangunan-bangunan yang lahir sebelum era standar yang diterbitkan oleh Kementerian PUPR. Nah, untuk itulah pada kesempatan hari ini kita ingin membuka pikiran kita untuk menyatukan langkah, melakukan satu perenungan dan memberikan masukan kepada pemerintah, khususnya terhadap bangunan-bangunan yang saat ini itu perlu mendapatkan perhatian, terutama bangunan-bangunan yang memiliki risiko tinggi terhadap masalah gempa. Risiko tinggi yang kita maksud saat ini adalah yang memberikan efek terhadap keselamatan publik. Oleh karena itu kami memandang penting Bapak staf ahli bahwa seminar hari ini dapat berlangsung dan memberikan masukan kepada pemerintah dan Bapak nantinya dan pada waktunya tentunya seminar ini tidak menjadikan satu seminar yang tanpa follow up, tanpa kelanjutan, tetapi seminar yang betul-betul memberikan masukan kepada pemerintah apa yang harus dilaksanakan terhadap situasi yang sekarang ada di Indonesia. Saya kira demikian laporan kami kepada Bapak staf ahli dan kami mohon dukungan kepada pemerintah untuk terus melanjutkan langkah kita, memberikan masukan kepada pemerintah, memberikan dukungan kepada pemerintah yang terkait dengan rekayasaan gempa, sehingga kita dapat memitigasi hal-hal yang akan terjadi jika gempa ini mengalami daerah-daerah kritik kita. Saya kira demikian yang bisa kami laporkan Bapak staf ahli, dan selanjutnya kami mengucapkan selamat atas terselenggaranya seminar ini dengan baik. Semoga seminar ini dapat memberikan manfaat dan kami juga mengucapkan terima kasih kepada Ketua Umum PII yang telah memberikan dukungan pada seminar ini dan kami mohon nantinya berkenan untuk memberikan sambutan, mengantarkan seminar ini menjadi bagian yang penting di dalam program PII, khususnya pertanggungjawaban terhadap profesi sebagai engineer. Saya kira demikian, kiranya terima kasih dan jika ada hal-hal yang kurang berkenan di Bapak dan Ibu sekalian, kami mengucapkan mohon maaf yang sebesar-besarnya dan akhirul kata wabillahi taufik wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih banyak kepada Bapak Sutopo atas sambutannya. Kami persilahkan untuk kembali ke tempat. Kalau tadi Pak Sutopo menyampaikan, kita boleh highlight ini adalah bagaimana peran dari profesi keinsinyuran untuk menghadapi kasus kegempaan, mulai dari efek gempa dan respon pasca terjadinya gempa dan memberikan masukan ya kepada pemerintah terkait dengan bangunan yang memiliki resiko tinggi terhadap gempa. Mr. Sutopo said that the goals of this event is to know how is the role of the engineering professions to face the earthquake. This role is start from the evac and respond after the earthquake happen and give the perspective to the government about the building that have the high risk of the earthquake. Selanjutnya kita akan mendengarkan sambutan dari staf ahli Menteri PU Bapak Endra S. Atmajaya. Kami persilakan Pak Endra. The next agenda is welcoming speech from Assistant of Public Works Ministry, Mr. Endra S. Atmajaya. Time is yours.
Baik, bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi Bapak Ibu, rekan-rekan semua. Pak Topo, Pak Sutopo Kristanto, Ketua Badan Kejuruan Teknik Sipil, PI, juga Bapak Ibu para narasumber, para pembicara. Ini ada Pak Tim Zapia, welcome to Jakarta, and also Pak Isak Ting, also welcome to Jakarta, and other speakers. Ini Pak Fahmi, selamat pagi, ke Pak Bambang Suendro, Pak Yosia, terima kasih, dan juga seluruh peserta Zoom. Jadi pagi ini saya tidak mempersiapkan diri untuk bicara, jadi karena tidak ada persiapan, tapi saya coba sampaikan beberapa hal. So Pak Tim, Pak Isak, I'm not the expert in this field, so I'm not the expert in geological survey or in the earthquake engineering, but I would like to deliver some experience that we have in a few years behind, ya, in Indonesia and also in the other places in the world. Kita melihat bahwa beberapa kota mengalami dampak yang dahsyat karena gempa, ya. Beberapa waktu yang lalu kita melihat gempa di Turki 2023, earthquake in Turkey. So it was very devastating earthquakes with more than 4,000 people died, and also buildings, public facilities are destroyed in a very vast area, Turkey and Syria. And then a bit recently in Morocco, a few weeks ago, yeah, I think more than 3,000 people are died because of the earthquakes. Di Indonesia kita tahu di Cianjur itu sekitar 600-an, kemudian di Lombok yang besar, ya, 2018 in Lombok, we have also the very severe earthquakes, very fast area impacted. So with around 500 people are died, but the economic damages, economic loss is very significant, very massive, ya, because of the earthquakes. Jadi memang kita melihat dua sisi, Bapak Ibu. Yang pertama adalah penyebab gempa ini ke manusianya dan juga ke orangnya. Gempanya bisa sedikit dari skala Richter, tapi dampaknya bisa dahsyat. So we can see the correlation between the magnitude of the earthquakes and the impact, but not necessarily always tidak selalu konsisten. Kalau gempanya besar, dampaknya juga besar. In Turkey and Syria, I think the magnitude is not so high, ya, around 5 and maybe below 5 in scale Richter. Tapi di penyebabnya sampai 40.000 dampaknya. Tapi kalau kita lihat di mana, di Lombok itu di atas 6, mungkin 7, ya Pak Fahmi, ya, nanti Bapak koreksi, ya. Itu dampaknya tidak terlalu besar. Jadi yang menyebabkan gempa itu menimbulkan dampak bukan gempanya sendiri, tapi bangunannya, strukturnya. Jadi we died because of the structure, not because of this earthquake. So this is also happening in Indonesia. The earthquake is quite high in terms of its magnitude in scale Richter, but the impact we can control because of the, sometimes because of the local wisdom of the structure of the houses, because they built with certain kind of wood material, which is quite flexible to respond, to absorb the earthquakes. Jadi ini pelajaran penting yang kita bisa catat, ya. This is very important lesson for us to make good decisions, to make good policy in order to reduce the risk of the earthquakes. Nah, kenapa? Karena kita tidak bisa mengantisipasi sepenuhnya earthquake ini. So we cannot anticipate 100%, when the earthquakes comes in how many magnitudes, the scale of the magnitudes, we cannot anticipate. So once when I traveled from Jakarta to maybe to Dubai, I saw a movie, San Andreas. Maybe you know the movie, yeah? The earthquake is in the eastern part of America, San Andreas, and the first time the impact was the overdam. Am I correct, Pak? Ini, you are from America, ya? Jadi ada bendungan besar itu yang terkena dampak dari gempa, Hoover Dam. Jadi San Andreas itu sampai ke California itu. Jadi kota-kota besar di California itu kena semua. Itu sebetulnya early warning ya for the American society about the possible impact of atau probable impact of the San Andreas bukan rekahan, patahan San Andreas Fault, ya. So the impact is very massive, ya. We can see, ya, we can see from the movie the lesson. Jadi ini semua bisa terjadi dimanapun yang namanya gempa. So Pak Tim, ya, and Pak Ishak, we are now constructing 61 dams in Indonesia, new dams within the last 10 years. 61 dams. So it varies, yeah, in terms of its size, of its storage capacity for these dams. But the interesting thing about this dam is that they are located in the tempat-tempat patahan itu. There is no one dam is free from the earthquake risk, disasters of earthquake. Itu, jadi ini bahwa semua dam kita itu ada di daerah patahan, betul nggak Pak Fahmi itu? Ada yang di daerah yang tidak ada patahannya, jadi semua itu bisa ada di gerakan tanah tinggi, landslides, patahan dan sebagainya. Jadi ini tantangan besar yang kita harus hadapi dan harus kita respon dengan kebijakan yang tepat, kemudian juga rekayasa engineering yang tepat. Dan satu lagi, kota-kota kita juga mulai. So we are now entering the urban area. So our cities are accelerating their development. So they start to build more high-rise buildings rather than landed buildings in our cities. We have nowadays 60% of people living in the urban areas. Since 10 years ago, we start to enter the urban era in Indonesia. So we have limited land space, limited space, where we start to build higher and higher. So this is also the challenge for the engineers to make a good structure of the buildings and also to address the earthquakes risk disaster. Nah, ini juga penting karena kota-kota kita seperti pelajaran tadi dari Turki itu kotanya meninggalnya bukan karena gempanya tapi karena bangunannya. Jadi itu juga satu hal yang saya kira perlu dicatat untuk kita bisa dengan baik merespon hal-hal tersebut. Jadi Bapak Ibu, sekali lagi saya menyambut baik apa yang diinisiasi oleh PII, oleh Badan Kejuruan Sipil, Pak Topo dan tim, dan saya kira ini kami tunggu hasil-hasilnya, saya kira nanti dalam bentuk rekomendasi ataupun dalam bentuk kegiatan real, ya, bagaimana misalkan kita memperkuat proses antisipasi gempa, kemudian kita juga dengan early warning system, kemudian kita juga memperkuat zoning regulations. This is also very important, Pak Ishak, ya, dan Pak Tim. Zoning regulations, we are a little bit not aware of these strong tools, ya, not structural but non-structural measures in reducing disaster risk of earthquakes. So zoning regulations, what we can do with the spatial planning to divide spaces into some zoning, red zones, orange zones, yellow zones, and also the green zones. It is also very important because people tend to forget very soon about the earthquake impacts. Yeah. So they think that the earthquake will come again in 10 years, 20 years, maybe 100 years from the actual occurrence. So I think this is also very important. We adopt the engineering recommendations into zoning. So because there is somehow to make a clear connection between engineering recommendations and the zoning to be adopted in the public policy. So this is also very important things that we have to address, how to make connections between the engineers and the planners. Engineers cannot do alone without planners, and planners would have to have recommendations from the engineers. So these two professions have to collaborate to make the earthquake response very effective measures and policy. Saya kira itu Pak Topo, Bapak Ibu yang bisa kami sampaikan. Mudah-mudahan ini bisa menjadi satu hal yang baik gitu ya. Saya lihat ada anak-anak muda di belakang. Ya ini we have young engineers behind Pak Topo, dilihat itu Pak Tim. So please belajar ya teman-teman, itu dari acara seminar hari ini diberi kesempatan, ini mahal seminar-seminar seperti ini. Jadi tolong dimanfaatkan dengan baik untuk kita bisa belajar dari Pak Tim, dari Pak Ishak, Pak Prof. Bambang Suhendro, Pak Fahmi, juga Pak Irwan ya. Saya kira ini kesempatan yang bagus untuk kita belajar. So I tell them to follow the today's session, today's seminar, because this is expensive. The lessons learned from Pak Tim ya, they're coming from very far away from here, from America and from Taiwan. This is very expensive lessons, teaching sessions. So we have to make the best use of their presence here. So I thank you Pak Tim, Pak Ishak for having you here in Jakarta in our ministry. Semua Pak Fahmi ya, Pak Irwan juga terima kasih. Bapak Ibu semua terima kasih. Pak Topo selamat atas seminarnya. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih banyak untuk Pak Endra. Kami persilakan untuk kembali ke tempat. Selanjutnya kita akan mendengarkan sambutan dari Ibu Rina Hubertus selaku perwakilan dari PT Tamara. Kami persilakan kepada Ibu Rina. And the next agenda is welcoming speech from PT Tamara representative, Mrs. Rina Hubertus. Time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sejahtera bagi kita semua. Puji syukur kita masih diberikan kesempatan untuk hadir bersama-sama di Kementerian PUPR ini dalam kondisi sehat walafiat. Yang pertama, kami ingin memperkenalkan perusahaan kami, PT Tamara Overseas Corporindo yang berdiri sejak tahun 1978, yang mana kami adalah agen tunggal dari produk MTS Amerika, dan salah satu produk range-nya adalah alat uji kegempaan simulasi. Dan yang kedua, kami mengucapkan terima kasih kepada PII, Bapak Sutopo dan teman-teman, kepada Kementerian PUPR yang sudah memberikan kesempatan pada kami untuk bisa hadir bersama-sama mengikuti seminar Rekayasa Kegempaan 2023, yang mana kami juga sudah mendatangkan pembicara kami dari MTS langsung, yaitu Mr. Tim Zapia dari MTS Amerika dan Mr. Isaac Ting dari MTS Taiwan. Kami juga mengucapkan terima kasih kepada rekan-rekan PII yang sudah menyiapkan acara ini dari awal sampai saat ini. Mudah-mudahan acara kita berakhir dengan baik, dan mudah-mudahan kami selaku PT Tamara dan selaku agen tunggal dari produk MTS dapat memberikan kontribusi yang terbaik untuk di kalangan PUPR ini. Mungkin itu aja yang dapat saya sampaikan. Wabillahi taufik wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Boleh kita minta tepuk tangannya. Terima kasih banyak pada Ibu Rina. Kami persilakan untuk kembali ke tempat. Ya, selanjutnya kita akan mendengarkan sambutan dari Bapak Danis Hidayat Sumadilaga selaku Ketua Umum PII. Kami persilahkan untuk Bapak Danis.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera untuk kita semua. Om Swastiastu, Namo Buddhaya, salam kebajikan. Pertama-tama marilah kita panjatkan puji syukur kehadirat Allah Subhanahu wa taala yang telah memberikan kesempatan pada kita semua untuk hadir pada acara yang luar biasa ini. Tentu saja atas nama Persatuan Insinyur Indonesia (PII), saya mengucapkan selamat dan sukses kepada para penyelenggara yaitu Badan Kejuruan Sipil Persatuan Insinyur Indonesia (PKSPII) yang bekerja sama dengan Kementerian PUPR, kemudian Tamara Overseas Corporindo dan juga MTS atas terselenggaranya kegiatan acara ini. Bapak Ibu sekalian, negara-negara di dunia termasuk Indonesia sedang banyak menghadapi tantangan yang diakibatkan oleh natural hazard dengan intensitas yang diketahui semakin ekstrim. Di antaranya adalah bahaya gempa, tsunami, pergerakan tanah, likuifaksi, perubahan iklim, dan lain-lain sebagainya. Salah satu tantangan terbesar Indonesia adalah lokasi Indonesia dekat Ring of Fire. Tantangan tersebut dibarengi dengan variabilitas kondisi dan parameter desain, termasuk geologi rentan likuifaksi di beberapa daerah. Bank Dunia pun memperkirakan Indonesia membutuhkan sekitar 300 sampai 500 juta dolar setiap tahunnya dalam rekonstruksi bangunan dan infrastruktur akibat gempa. Bapak Ibu sekalian, PII adalah institusi yang menerima mandat dari pemerintah untuk mengembangkan kompetensi insinyur dan insinyur profesional Indonesia untuk menjadi lebih kompeten, yang kemudian diberikan peran untuk berkontribusi pada perkembangan rekayasa kegempaan untuk melakukan minimalisasi ataupun mitigasi kerugian kegagalan bangunan sebagai topik yang akan dilakukan untuk seminar ini. Reduksi resiko bencana memerlukan kesiapan dan kolaborasi multidisiplin. PII bersama pemerintah dan semua kelompok masyarakat harus berkolaborasi untuk mencapai level ketangguhan terhadap bencana di seluruh lapisan masyarakat. Dari 10 mata rantai manajemen risiko bencana atau Disaster Risk Reduction Management Plan, Insinyur Indonesia setidaknya terlibat pada 5 aktivitas, antara lain penyiapan dan penyusunan building infrastruktur standar and code, sosialisasi terhadap code tadi, kemudian building infrastructure design, kemudian building infrastructure code compliance, dan juga construction supervision. Bapak Ibu sekalian, tentu saja hal ini memerlukan suatu upaya yang terus-menerus diantaranya oleh PII untuk melakukan sosialisasi hal tersebut. Izinkan sebagai Ketua Umum PII, saya juga saat ini diberikan amanah sebagai Chairman of AVEO, ya, mendapatkan kesempatan untuk menjadi tuan rumah Conference of AVEO atau KVEO 41 di Bali pada tanggal 21-23 November ini. KVEO menjadi wadah buat para ASEAN engineer untuk sharing knowledge and experiences, melakukan networking, dan juga menghadirkan business opportunity antar sesama insinyur ASEAN. Kami mengundang kawan-kawan semua dan seluruh insinyur Indonesia untuk mengikuti acara KVEO ini. Selain hal tersebut, dapat kami sampaikan juga mengenai beberapa perkembangan terhadap institusi PII ini, ya, yaitu seperti kita ketahui bahwa PII menjadi bagian dari International Engineering Alliances sejak 2002. Kemudian melalui IAB, Indonesian Accreditation Board of Engineering Education, PII telah menjadi full signatory member of Washington Accord. Saat ini juga dapat kami laporkan bahwa terdapat kenaikan secara signifikan keanggotaan PII menjadi sekitar 81.000. Terima kasih kepada semua institusi yang telah mendukung keanggotaan PII ini. Selain itu, peningkatan insinyur profesional yang sudah kurang lebih 27.000 dan di dalamnya termasuk ratusan insinyur asing yang berpraktek keinsinyuran di Indonesia. Kemudian teman-teman sekalian, insinyur terregistrasi ASEAN Engineering menjadi sekitar 2.300 orang. Selain itu, dalam rangka mendukung wawasan kita agar lebih global, PI telah membuka beberapa chapter atau membentuk beberapa chapter luar negeri di Singapura, Malaysia, Kuwait, Amerika Serikat, dan Australia. Kemudian, dukungan terhadap program profesi insinyur akan terus kami tingkatkan, yang pada saat ini lulusannya sudah sekitar 18.000 insinyur yang mengikuti program PSPPI ini. Selain itu, yang terakhir, kami juga telah menandatangani Mutual Recognition Agreement dengan Engineer Australia (EA) sebagai wujud kerjasama ekonomi antara Indonesia dan Australia, di mana Mutual Recognition Agreement ini menjadi salah satu penting dari joint communique yang disepakati antara Indonesia dan Australia dan diumumkan pada saat Presiden kita Joko Widodo melakukan kunjungan kenegaraan di Australia awal Juli kemarin. Bapak Ibu sekalian, kembali kepada acara seminar ini. Sekali lagi selamat melaksanakan seminar ini. Sekali lagi juga terima kasih kepada pengurus BKSPI, Pak Sutopo dan tim, kemudian juga Kementerian PUPR dan teman-teman yang lain, dan tentu saja kepada para peserta yang hadir hari ini. Semoga Allah Subhanahu wa Ta'ala, Tuhan yang Maha Kuasa, senantiasa membimbing dan melindungi langkah kita semua dalam mewujudkan cita-cita kita bersama. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh. Terima kasih.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih banyak Bapak Danis Hidayat Sumadilaga selaku Ketua Umum PII. As we know that Mr. Danis Hidayat as a Chairman General PII said that Indonesia's condition is in the ring of fire, so it can give the impact of the earthquake. So we have to make a strategy to face it. One of the strategy that Mr. Danis Hidayat said is all about the building infrastructure design. And the next agenda atau agenda selanjutnya, yaitu kita akan mendengarkan sambutan dari Kepala Balai Geoteknik Terowongan dan Struktur, Bapak Fahmi Aldimar. Kami persilahkan. The next agenda is welcoming speech from Mr. Fahmi Aldimar as a head of Geotechnical Center. Time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera bagi kita semua. Yang terhormat Bapak Staf Ahli Menteri PUPR, Bapak Endra Wijaya, kemudian Ketua Umum PII, Bapak Danis Sumadilaga, kemudian Bapak Sutopo. Izin pada kesempatan pagi ini saya akan memberikan sedikit pemaparan, mungkin sedikit overview terkait dengan kegempaan dan juga tantangan insinyur Indonesia. Jika dibolehkan izin, apakah bisa ditayangkan oleh panitia? Baik, yang ingin saya sampaikan di sini adalah mungkin lingkup-lingkup terkait dengan kegempaan, tantangan kita ke depan, dan standar ataupun pedoman yang sudah kita miliki sebagai panduan bagi rekan-rekan semua, terutama di keinsinyuran, dengan harapan bahwa dengan meningkatnya kapasitas ataupun kemampuan SDM di kita, otomatis bangunan ataupun infrastruktur yang di kita juga akan lebih handal. Next. Next. Baik, Bapak Ibu sekalian, ini adalah hal yang sudah menjadi pertimbangan kita semua. Dalam artian pada saat kita bicara kegempaan, maka kondisi alam ini yang harus kita hadapi. Jadi kondisi tektonik kita di sini cukup kompleks. Jadi secara umum bahwa kita ada 4 lempeng yang bergerak dan masing-masing memiliki laju pergerakan yang cukup tinggi. Jadi apabila kita lihat di Indo-Australia dia menunjam ke arah ke lempeng Sunda kurang lebih 6 cm per tahun. Jadi akan ada akumulasi energi setiap tahunnya akibat pergerakan tersebut, dan suatu ketika apabila energi itu terlepas maka gempa itu akan terjadi. Next. Ini adalah lempeng-lempeng utama tadi yang ada di sekitar Indonesia yang juga mewarnai kondisi kegempaan yang ada di kita. Next. Dan apabila kita lihat, ini adalah data-data kejadian gempa sebarannya di seluruh Indonesia. Jadi kalau kita lihat hampir seluruh pulau yang ada di Indonesia ini tertutupi oleh data kejadian gempa. Ini menunjukkan betapa kita harus sudah mulai berpikir bahwa infrastruktur kita harus lebih aware ataupun lebih tahan terhadap kegempaan tersebut. Kita harus mengantisipasi hal-hal yang sudah tidak mungkin lagi terelakkan. Jadi kegempaan ini adalah hal yang pasti terjadi. Kapan kita tidak tahu, tetapi secara historis ini 100 tahun ke belakang apabila kita plotkan datanya, seluruh kondisi yang ada di Indonesia ini tertutupi oleh kejadian gempa tersebut. Lanjut. Apabila kita lihat juga ini adalah data dari kejadian bencana yang ada di Indonesia dari tahun 2005 sampai 2014. Apabila kita lihat ke yang 2023 ini juga akan meningkat. Jadi dominannya ini adalah 31% runtuhnya bangunan itu akibat dari bencana gempa bumi. Ini mungkin tadi sudah disampaikan oleh Bapak Staf Ahli Menteri bahwa memang betul kejadian gempanya tidak mungkin kita elakkan, tetapi bangunan yang akan menjadi penyebab terjadinya fatalities atau terjadinya korban jiwa. Jadi kondisi struktur bangunan kita ini apabila tidak kita perbaiki, ini akan berdampak lebih lanjut terhadap kematian ataupun ke korban jiwa. Kemudian 5,2% kematian ini akibat dari bencana gempa bumi, baik itu dari tsunami ataupun bencana lainnya, terutama likuifaksi. Lanjut. Kemudian ini adalah lingkup yang mungkin saya ingin coba share. Jadi sebagai konseptual, apa yang ada di SNI, apa yang ada di standar yang sudah kita bakukan, ini kita harus mengetahui apa itu parameter gempa untuk kebutuhan perencanaan. Lanjut. Ini mungkin secara overall, next dulu. Lanjut. Nah, jadi apabila kita lihat kegempaan ini memang kita sudah tahu pasti akan terjadi. Kita belum tahu di mana dan berapa besarannya, jadi kita belum bisa melakukan forecasting, mungkin di luar pun belum bisa melakukan sedetail ataupun seefektif itu, sehingga kita sudah sama-sama meyakini bahwa kejadian gempa ini tidak dapat dicegah. Sehingga kalau kita bicara bahwa fatalities harus kita kurangi, manusia harus kita lindungi, ini mengacu pada FEMA, kita harus mengidentifikasi sumber gempanya. Jadi ini sudah dilakukan oleh Pusat Nasional Gempa, ini sudah kita coba petakan, di mana sesar-sesar aktif yang ada di Indonesia, mungkin tadi juga disampaikan oleh Bapak Staf Ahli Menteri, contohnya di San Andreas, itu harus dipetakan dengan persis di mana posisi sesar aktifnya, kemudian dibuat perambuan dengan tujuan bahwa jangan sampai kita membangun infrastruktur di daerah yang berpotensi mengakibatkan kerusakan, baik itu bangunan dan juga korban jiwa. Kemudian tsunami ini adalah bagian dari efek dari gempa, otomatis juga kita harus bisa memetakan zona mana saja yang rawan terhadap tsunami dan kita juga tidak membolehkan adanya bangunan ataupun kita harus mengantisipasi dengan bangunan-bangunan yang bisa menahan terjadinya tsunami atau mereduksi dampak yang akibat tsunami tersebut. Kemudian likuifaksi ini seperti halnya kita lihat di Palu, ini juga bisa mengakibatkan dampak yang besar akibat material tanah yang mengalami penjenuhan dan kemudian dia mengalami kekurangan geser dan dia pada saat terdisplace atau mengalami pergeseran itu besarannya luar biasa sampai ratusan meter dan mengakibatkan dampak yang cukup besar pada bangunan dan juga pada korban jiwa. Kemudian seperti yang terjadi di Cianjur, korban terkait dengan longsoran ini juga sama. Jadi walaupun kita sudah mencoba mengantisipasi memetakan posisi sesar gempa, sesar aktif yang ada di Indonesia, tapi apabila kita lihat kejadian gempanya sangat banyak dan belum seluruhnya teridentifikasi. Contoh yang di Cianjur adalah salah satu contoh munculnya sesar baru yang dulu belum terantisipasi. Ternyata di situ ada zona sesar aktif yang memang harus kita masukkan juga ke dalam peta gempa nasional kita. Nah, ini yang menjadi dasar mengapa kita harus membuat bangunan kita tahan terhadap goyangan gempa. Lanjut. Kemudian kalau kita lihat di sini ada beberapa kondisi di mana terjadi kerusakan pada bangunan, terjadi kelongsoran. Lanjut. dan likuifaksi. Jadi pada prinsipnya adalah kalau kita melihat di sini ada suatu nilai parameter kegempaan, yaitu percepatan gempa yang memang harus diantisipasi pada perencanaan infrastruktur ataupun bangunan gedung yang ada di Indonesia. Nah, ini biasanya kita mengkorelasikan dengan nilai A atau percepatan. Ini mengacu pada hukum Newton kedua. Next. Nah, nilai-nilai percepatan ini sangat tergantung dari infrastruktur yang nanti akan kita desain. Jadi kalau kita bicara kebangunan gedung, ini terkait dengan tinggi dari bangunannya. Kemudian terkait dengan tanah, apabila kita bicara kelongsoran, maka ini sangat terkait dengan massa dari tanah yang nanti akan mengalami pergerakan. Dan apabila kita bicara ke kondisi likuifaksi, itu tergantung dari kondisi lapisan pasir yang jenuh air yang dapat memicu terjadinya tekanan uplift akibat dari potensi likuifaksi yang terjadi. Kemudian ini juga isu lainnya terkait dengan amplifikasi, Bapak Ibu sekalian, di daerah cekungan, ini terutama di daerah-daerah, khusus di daerah perkotaan yang cukup padat penduduknya. Ini contoh mungkin nanti akan saya coba sampaikan di Meksiko, terjadi peningkatan faktor percepatan dari batuan dasar ke permukaan yang cukup besar, yang awalnya kita mengira bahwa gempanya kecil, mungkin tadi hanya dari skala Richter 6 atau 7, itu di permukaan bisa teramplifikasi lebih besar sehingga dampaknya ke bangunan pun bisa mengalami keruntuhan. Lanjut. Kemudian ini adalah salah satu runutan Bapak Ibu sekalian. Jadi apabila kita lihat di sini standar kegempaan kita sudah menyusun dari tahun 92, kemudian kita lakukan update di tahun 2008 dan terakhir di 2016 ini sudah kita update kembali mengacu pada peta gempa tahun 2010. Tapi ini pun kita akan coba update kembali karena mungkin di tahun depan ini rencananya Pusgen akan mengeluarkan kembali peta gempa yang sudah terupdate. Nanti akan disinkronkan dengan standar kita terkait dengan gempa untuk jembatan, baik itu untuk bangunan gedung dan bendungan, dengan harapan bahwa seluruh peta yang nanti akan digunakan sinkron terhadap desain dari struktur bangunan yang akan kita bangun. Kemudian untuk jembatan sendiri ini ada suatu hal yang signifikan. Jadi yang pertama adalah ada seismic demand yang meningkat. Jadi yang awalnya umur rencana 50 tahun menjadi 75 tahun. Sehingga otomatis dari segi kekuatan bangunan pun akan lebih tinggi dibandingkan dengan bangunan sebelumnya. Lanjut. Ya, lanjut lagi. Nah, ini adalah salah satu contoh peta-peta yang sudah dihasilkan di peta sumber gempa dan peta kegempaan, terutama untuk yang dikeluarkan di tahun 2010. Lanjut, di sini adalah yang untuk di batuan dasar, kemudian di 0,2 detik dan satu lagi di 1 detik. Lanjut. Oke, lanjut. Lanjut. Nah, ini adalah salah satu lingkup yang membedakan antara acuan kita yang lama dari BMS 92 ke ASTO tahun 2013 pada saat itu. Lanjut. Nah, pada saat kita bicara di BMS, maka petanya adalah hanya satu peta saja di periode ulang 500 tahun. Kemudian kalau kita sandingkan dengan peta yang baru, ini ada 3 peta di batuan dasar di periode 0,2 detik dan di 1 detik. Lanjut. Lanjut. Nah, sehingga pada saat kita bicara pembuatan respon spektra desain, ini berbeda. Jadi yang pertama kalau kita lihat yang di sebelah kiri, respon spektra desainnya ini dibentuk dari nilai PGA saja. Sedangkan kalau kita lihat yang di sebelah kanan, lanjut, ini kita susun berdasarkan 3 poin sehingga dari segi akurasi akan lebih tinggi dan juga ini mengakomodir untuk periode 1 detik atau long period untuk bangunan, terutama di lingkup ini adalah untuk jembatan. Lanjut. Kemudian ini juga lingkup yang sedang kami susun, ini sedang dalam proses penyusunan dan juga evaluasi. Ini adalah untuk kebutuhan isolation design, jadi untuk kebutuhan retrofit. Ini juga kita sedang siapkan, tapi untuk lingkup yang ini adalah lingkup di mana kita bisa melakukan intervensi pada struktur supaya nilai percepatan yang terjadi bisa direduksi mempergunakan seismic isolation. Lanjut. Kemudian terkait dengan perkuatan jembatan pun ini memang kita sudah coba buat lingkupnya. Jadi kita bisa identifikasi jembatan-jembatan tipe apa saja yang ada di Indonesia mempergunakan aplikasi InVJ. Kemudian dari situ juga kita bisa melihat apakah jembatan-jembatan yang sudah terbangun masuk daerah dalam lokasi yang rentan terhadap gempa atau tidak. Sehingga nanti kita bisa membuat suatu mitigasi, suatu perkuatan-perkuatan yang diperlukan untuk menjaga bahwa jembatan ini akan tetap fungsional pada saat terjadi gempa. Ini contohnya, jadi kalau kita lihat bahwa perlu ada perkuatan di bagian pilar, maka kita bisa melakukan jacketing. Kemudian pada saat kita lihat bahwa ternyata dari segi tumpuan atau peletakannya perlu ada tadi untuk mengurangi beban yang bekerja pada struktur atas ataupun pada pilar, ini kita bisa ubah antara yang awalnya elastomer biasa menjadi seismic isolation, misalnya menggunakan LRB, kemudian ada restraining cable dan lain sebagainya. Ini adalah lingkup-lingkup yang nanti kita bisa gunakan tergantung dari perkuatan yang diperlukan ataupun seberapa dekat bangunan yang kita miliki berada di daerah yang aktif atau tidak terhadap zona gempa tersebut. Lanjut. Mungkin ini adalah salah satu contoh Bapak Ibu sekalian. Ini adalah jembatan Palu 4 dan jembatan Dolago. Jadi apabila kita lihat di sini gempa yang terjadi di Palu cukup besar. Jadi besarannya bisa sampai dengan mendekati 0,5 G dari hasil catatan di akselerometer. Dan dapat dilihat juga bahwa kerusakan yang terjadi di sini cukup parah. Ini kerusakan pada bagian perletakan dan juga ada jembatan yang mengalami keruntuhan. Jadi ini memang PR kita berikutnya adalah kita harus melakukan pemeriksaan dan evaluasi perkuatan apa saja yang perlu kita lakukan untuk jembatan-jembatan yang sudah terbangun. Lanjut. Nah ini sebagai contoh, ini apabila kita lihat Bapak Ibu sekalian, ini adalah peta gempa yang lama yang mempergunakan periode orang yang 500 tahun. Jadi apabila kita lihat di sini besaran percepatan gempanya hanya 0,2 G, sedangkan kalau kita lihat kejadian yang terjadi di sini dengan kejadian gempa di magnitudo 7,4, percepatan yang terjadi ini cukup besar. Ini dari data akselerometer kita melihat ada dua komponen, utara selatan dan juga barat timur. Ini utara selatannya sampai dengan 0,67 G, sedangkan barat timurnya 0,49 G. Jadi jika kita lihat terhadap kriteria beban gempa yang ada pada saat itu, ini sudah kategorinya underestimate. Jadi nilai yang ditentukan oleh desain itu lebih rendah daripada kejadian yang terjadi. Lanjut. Nah kalau kita lihat apabila kita menggunakan peta yang 2010 ataupun 2017, dapat kita lihat bahwa besaran gempa yang memang perlu diantisipasi di sini adalah 0,9 sampai dengan 1 G, tapi nanti akan ada faktor reduksi tergantung dari kodenya. Sehingga memang umumnya kalau kita mempergunakan peta gempa yang baru, maka pada saat kejadian ini terjadi, bangunan kita akan lebih tahan terhadap gempa. Jadi yang ingin saya coba tekankan di sini adalah tolong sama-sama kita pelajari kembali SNI kita dan juga peta gempa yang terbaru. Tujuannya adalah supaya kita lebih aware bahwa tidak serta-merta bahwa beban gempanya meningkat, otomatis biaya ekonominya meningkat ya untuk pembangunan, tetapi dari segi ketahanan dan juga keamanan terhadap konstruksi juga akan lebih handal. Lanjut. Nah ini mungkin salah satu isu lain, jadi untuk kasus-kasus di daerah cekungan. Jadi kalau kita lihat di batuan dasar ini besaran kecepatan gempanya akan meningkat bisa sampai 4-5 kalinya di permukaan jika kita meninjau bahwa daerahnya adalah daerah yang memang daerah cekungan atau ada kayak semacam basin effect, di mana ada kayak semacam mangkuk. Kalau kita berikan goyangan, maka goyangan itu akan teramplifikasi atau akan meningkat secara besar dikarenakan memang kondisinya adalah kondisi yang khusus. Jadi memang seperti halnya di daerah Jakarta yang memang ada daerah cekungan, apabila terjadi gempa besar ini juga kita harus hati-hati. Di daerah Bandung, Semarang dan lokasi lainnya yang memang dari segi populasinya cukup tinggi, ini adalah isu lainnya. Jadi ada kondisi khusus di mana kalau untuk kondisi di mana dia daerahnya adalah daerah cekungan, kemudian tanah lunaknya cukup dalam, nah, efek-efek amplifikasi ini yang memang harus kita antisipasi. Lanjut. Nah ini juga kita sudah mencoba mengantisipasi di dalam standar kita. Jadi apabila kita memiliki suatu nilai percepatan di batuan dasar, lanjut. Nah, ini akan ada suatu faktor yang kita kalikan dengan faktor percepatan di batuan dasar, sehingga pada saat kita mendapatkan spektra desain di permukaan, ada faktor pengali untuk kebutuhan keamanan kita dari segi bangunan ataupun infrastruktur jalan dan jembatan. Tujuannya adalah tadi, apabila kita melihat bahwa kondisi tanahnya adalah kondisi tanah yang khusus, maka faktor amplifikasi itu akan memberikan nilai margin keamanan supaya struktur kita atau infrastruktur kita akan lebih handal atau lebih aman. Lanjut. Nah, ini adalah kriterianya Bapak Ibu sekalian. Jadi kalau kita lihat ada kategori di mana kita bisa menentukan apakah itu kategorinya adalah tanah lunak, tanah sedang, ataupun batuan. Ini didasarkan dari hasil penyelidikan lapangan atau penyelidikan tanah, dan di situ kita bisa menentukan apakah kategori yang kita hadapi adalah kategori khusus atau tidak. Nah, kalau kategori khusus, maka kita harus melakukan suatu analisis khusus supaya bangunan kita akan lebih aman. Lanjut. Oke, lanjut. Nah, ini adalah salah satu contoh Bapak Ibu sekalian di Jembatan Kretek. Jadi apabila Bapak Ibu sempat mengunjungi ke sana, jadi di sana sudah dipetakan ada sesar opak yang berada di daerah abutmen jembatan. Jadi di situ sudah diantisipasi kalau terjadi gempa di kemudian hari akibat gempa dari sesar opak, dimungkinkan ada kerusakan tetapi tidak sampai mengakibatkan putusnya ataupun terhentinya dari fungsional dari jembatan tersebut. Lanjut. Nah, selain itu juga di bagian perletakan ini juga ada suatu penggunaan isolation seismik tadi ya, tim pergunakan LRB. Jadi jembatan ini sudah mengacu pada SNI 2833 2016 dan memang sudah ada penahan tambahan di sini ya berupa isolasi seismik yaitu LRB. Next. Nah, ini mungkin sebagai gambaran Bapak Ibu sekalian bahwa LRB ini secara visual kurang lebih seperti ini. Jadi ada karet di bagian dalam yang kemudian ada lead core-nya, ini berupa inti timbal. Sehingga tujuannya adalah pada saat dia mengalami goyangan gempa terhadap horizontal, maka timbal ini akan mengalami panas sehingga dia akan mencair. Nah, pada saat dia mengalami goyangan, dia akan memiliki kelenturan ya, dia mengikuti gaya gempanya. Kemudian pada saat goyangan gempanya sudah selesai, dia akan kembali ke posisi semula dan timbalnya akan mendingin kembali atau menjadi keras kembali. Nah, ini harapannya adalah pada saat ada goyangan gempa itu akan direduksi oleh LRB ini. Kemudian sebagai informasi juga bahwa LRB ini sudah diproduksi lokal, jadi dimungkinkan untuk digunakan dan alat ujinya pun sudah ada di Indonesia. Lanjut. Nah, ini secara konseptual Bapak Ibu sekalian, jadi apabila kita bicara pembangunan jembatan dengan pilar yang cukup tinggi, maka beban gempa ini bisa mengakibatkan terjadinya suatu goyangan kedua arah, bolak-balik atau cyclic pada struktur yang mengakibatkan apabila struktur tersebut tidak cukup kuat, maka akan mengalami kerusakan, retakan, dan mengakibatkan terjadinya keruntuhan. Nah, apabila kita menggunakan seismic isolation, maka goyangan gempa itu akan direduksi sehingga hanya bagian struktur atasnya saja yang bergoyang, tetapi tidak mengalami kerusakan pada bagian struktur kolomnya. Lanjut. Kemudian terkait dengan penggunaannya, jadi Bapak Ibu sekalian ini juga kami sampaikan, kita sudah keluarkan ada spesifik khusus interim dari Direktorat Jenderal Bina Marga. Nah, di sini memang spesifik kita memberikan acuan untuk kebutuhan penggunaan LRB. Di dalamnya ada penjaminan mutunya, kemudian ada toleransi manufacture, ada standar rujukan, sampai dengan pedoman pemasangan dan pengukuran ataupun pembayarannya. Jadi dari segi lingkup, item pekerjaan ini sudah bisa digunakan dan sudah bisa dibayarkan dengan jaminan mutu sesuai lingkup yang ada di dalam spek tersebut. Lanjut. Ini adalah akhir dari sesi yang saya coba tayangkan. Jadi secara overall adalah bahwa kita sama-sama ketahui kita berada di kondisi yang rentan terhadap beban gempa, sehingga mau tidak mau kita harus membuat suatu kategori di mana struktur kita akan lebih tahan terhadap gempa. Salah satunya adalah dengan pembuatan standar ataupun pedoman ataupun spesifikasi teknis. Kemudian yang menjadi kunci adalah tantangan bagi kita semua, bagaimana caranya kita supaya keep up atau mengikuti aturan-aturan yang terbaru. Jadi jangan sampai kita tertinggal sehingga apa yang seharusnya kita antisipasi ini terlewatkan. Ini demikian yang bisa saya sampaikan. Terima kasih atas perhatiannya. Assalamualaikum warahmatullahi wabarakatuh.
Baik, terima kasih banyak untuk Pak Fahmi. Kami persilakan untuk kembali ke tempat. Sebelum kita melanjutkan acara, kita boleh terlebih dahulu, ini sesi foto bersama. Kita boleh minta bantuan untuk panitia bisa memandu jalan sesi foto bersama. Kami persilakan untuk seluruh narasumber yang hadir pada pagi hari ini untuk maju ke depan. Kami persilakan. Kami turut mengundang Pak Endra, kemudian Pak Kimron Manik, kemudian Pak Sutopo, Pak Fahmi, Pak Elmiko untuk sesi foto bersama terlebih dahulu. Oke. Mungkin panitia boleh dibantu jalanin sesi foto bersama. Ya, ini harus memberikan senyum yang terbaik ya. Kita hitung 1 sampai 3. 1, 2, 3. Ya. Sekali lagi. 1, 2, 3. Salam tangan dulu. Oh, katanya salam tangan dulu. Kami persilahkan. 1, 2, 3. Baik. Sudah cukup teman-teman? Oke. Kami persilahkan untuk Pak Endra, Pak Kimron, Pak Sutopo, Pak Fahmi, Pak Elmiko, dan Bapak Ibu yang sudah di depan. Kami persilahkan untuk, ya, dipersilahkan untuk langsung menuju ke depan. Oh, boleh foto di bagian sini Pak? Oke, kami persilahkan. Mungkin panitia boleh dibantu ya, jalanin sesi foto bersama. Kami sekali lagi. Oke, jadi bapak-bapak, ibu-ibu kami persilahkan untuk berdiri sebentar. Menghadap ke layar yang di depan. Nah, tim panitia foto dari sini, kurang lebih gitu ya Pak ya? Oke, mantap. Sebentar, kita coba cek dulu semuanya sudah siap. Oh boleh, tangannya gini ya Pak. Oke. Kita hitung, 1, 2, 3. Sekali lagi, 1, 2, 3. Oh masih satu lagi. Oke, boleh tambah satu lagi. 1, 2, 3. Mantap. Terima kasih banyak, boleh minta tepuk tangannya sekali lagi untuk kita semua. Kami persilakan untuk bapak-bapak, ibu-ibu yang ada di sini, kita bolehkan untuk misalnya kalau mau rehat sejenak gitu, mau ngopi-ngopi boleh. Nanti sebelum kita lanjutkan sesi berikutnya itu adalah panel diskusi. Untuk Pak Fahmi, Pak Endra ini karena tidak bisa mengikuti acara sampai selesai betul ya Pak ya. Tapi terima kasih banyak atas kehadirannya untuk pagi hari ini. Terima kasih banyak, kita harapkan juga acaranya bisa berjalan dengan lancar. Oke, coffee break dulu ya. Terima kasih banyak sekali lagi atas kehadiran dari Pak Indra S. Atma Wijaya selaku staf ahli Menteri PU atas kehadirannya pagi hari ini. Dan untuk Bapak Ibu yang hadir di ruangan ini kami persilakan untuk ini rehat sejenak lah ya. Kurang lebih kita berikan waktu 2 menit. Selanjutnya kita akan langsung mulai acara panel diskusi berkaitan dengan tantangan Insinyur terhadap perkembangan rekayasa kegempaan untuk minimalisasi kerugian kegagalan bangunan. Sekali lagi kami ingatkan untuk Bapak Ibu yang hadir di ruangan ini, kami berikan waktu untuk menyantap hidangan, coffee break sejenak ya. Ini 1 hingga 2 menit dan kami mohon kesediaannya untuk kembali lagi ke tempat karena acara akan segera dilanjutkan, yaitu panel diskusi berkaitan dengan tantangan Insinyur terhadap perkembangan rekayasa kegempaan untuk minimalisasi kerugian kegagalan bangunan. Baik, untuk Bapak Ibu, kita akan segera melanjutkan agenda berikutnya yaitu panel diskusi. Kami mohon kesediaannya untuk Bapak Ibu yang sudah hadir di ruangan untuk kembali menempati tempat duduk yang sudah kami siapkan. Ladies and gentlemen, we cordially invite you to gather at this venue because in a few minutes we will start the event of Earthquake Engineering Seminar. Thank you. Baik, kami ingatkan sekali lagi kepada Bapak Ibu yang sudah hadir untuk segera menempati tempat duduk yang sudah kami siapkan. Karena acara selanjutnya adalah panel diskusi, Pak Fahmi, kami persilakan untuk menempati tempat duduk yang akan dipandu oleh moderator kita, Bapak Yosia Irwan Rastandi. Baik, kalau sudah menempati tempat duduk yang sudah disiapkan, kami akan segera memulai acara. Ladies and gentlemen, we cordially invite you to gather at this venue because in a few minutes we will start this event for panel discussion. Please have a seat for all of the ladies and gentlemen. Oke, acara selanjutnya yaitu kita akan memasuki agenda panel diskusi mengenai tantangan Insinyur terhadap perkembangan rekayasa kegempaan untuk minimalisasi kerugian kegagalan bangunan yang akan langsung dipandu oleh Bapak Yosia Irwan Rastandi. Kami persilahkan.
Ya, selamat pagi Bapak Ibu sekalian yang ada di sini secara offline maupun yang ada secara online. Baiklah, saya akan memulai saja diskusi kita pada sesi kali ini. Jadi kita ada punya sesi tanya jawab selama 20 menit untuk tadi apa yang sudah dipaparkan oleh para pembicara kita di awal tadi, juga terutama dari Pak Fahmi, mungkin saya bisa buka sesi tanya jawabnya. Mungkin untuk penanya sesi pertama ini, untuk yang online saya bisa lihat di mana ya? Mungkin bisa. Oke, mungkin dari pertama untuk yang online dulu saya berikan kesempatan.
Izin Pak Yosia, mungkin sembari nanti kita menunggu kehadiran dari atau pertanyaan dari yang hadir secara online, mungkin kita boleh terlebih dahulu Pak untuk sesi panel diskusi ini dibagi beberapa tahapan. Mungkin yang pertama presentasi dari masing-masing narasumber terlebih dahulu, baru kemudian kita buka untuk sesi tanya jawab.
Soalnya di sini setelah Pak Fahmi, schedule-nya sesi tanya jawab.
Oke, baik. Kalau memang
di apa namanya, di rundown yang saya dapat ini setelah Pak Fahmi sesi tanya jawab.
Oke, kalau memang
Ataukah
tidak ada yang
mungkin
presentasi, kami langsung buka saja, tidak apa-apa Pak. Kalau memang tidak ada yang menyampaikan pemaparan materi. Tapi kalau ada yang berkenan untuk memaparkan materi, mungkin kita berikan waktu Pak.
Mungkin ada perubahan dari jadwalnya. Kalau begitu mungkin saya bisa sampaikan dulu ya untuk pemaparannya. Jadi untuk pemaparan yang pertama di sini, pemaparan dari Mr. Tim Zappa atau Isaac Ting. So I think for the next, we invite Mr. Tim Zappa or Mr. Isaac, Mr. Tim, okay, to have a presentation about 30 minutes, 70 minutes. You have 70 minutes. The floor is yours, please.
Hello? Okay. One moment while I set up my computer. So, good morning, and thank you very much for having us, and it's a real honor to be here. My name is Tim Zappa, and I work for MTS Systems that's headquartered in the US. I have been with the company for 33 years. It's been a wonderful place to work and a great career there. My background is in computer science, and then I've taken jobs as a controls engineer, a program manager, operations, and business development. And now I find myself, since 2009, as an applications engineer, primarily working on selling seismic systems around the world. So I will try to speak slowly, and hopefully my English will not be a problem. If you need me to slow down, tell me to slow down, and I will. So the agenda that we thought for today was something like this. But we thought there was more time, so we're going to condense it a little bit. But I wanted to tell you a little bit about MTS very quickly, real quickly now. Then about the seismic system fundamentals, the basic things behind them, why we build them, how we build them, and then give you some example systems for laboratories that we built around the world, and then some example applications about some work that people have been doing on. And then in the afternoon, we will show some examples of a workshop about how we actually use the tools that we develop. So, I don't know if everybody knows about MTS, but I will assume maybe not. So the company is located in Minnesota, which is in the center of the U.S. north. And we started in about 1966. And today we have about 1,700 employees worldwide. The thing about MTS is that we primarily are made of mechanical engineers, control engineers, and electrical engineers. That's primarily what we are, and we work on systems. And the thing that we try to do as good as we can do is we control very precisely forces and motions, because we want to replicate testing situations so that people can validate their designs and make them as best as possible. In the structural world, it's about making buildings safer, bridges safer, non-structural components safer, and the work that you guys do is, we feel really proud and very honored to be part of it, because you guys are saving lives, basically, and you're helping economies. So we do business about equally across the Americas, Europe, and Asia. As you can see here, a little bit more in Asia. And a lot of that has been coming out of China, which we'll talk about a little bit later. So we have three main businesses within MTS. We have ground vehicles, we have materials, and we have structures. So that's how we segment out our work, and we try to focus in each of those areas. Since time is tight, I won't talk a lot about this in detail. Let's see if this works here. I'll talk as this is playing. So what MTS, this is a video about some of the ground vehicles work that we do. But as it's playing, I will talk about some of the technology that we use everywhere. And basically, the idea is we take recorded real-world forces, displacements, velocities, and we play them out as precisely as possible into our test systems. And we do that by primarily something that MTS developed called remote parameter control, where we take the system that we built, and then we'll take the inverse of that, and we will correct for the errors of what we send out to the system versus what is really wanted. So we compensate for the system dynamics in order to get exact type of performance. So in the ground vehicles world, this is about enhancing performance and durability of all kinds of testing. This right here is about simulations where we can test a component, here dampers, and use a model of a full car. So the full car is simulated, and then we focus on the dampers, and we give the forces back into the model. It does its thing with the overall car, sends us new forces back. And we do that in structure stuff as well. So this idea of using numerical models and integrating it with the testing system is maybe the newest sort of testing that's been taking place. So as you can see on this video, every car manufacturer in the world will have an MTS system. Every component on that car is tested. And that's not just for cars, but it's for trains, it's for aerospace, airplanes, rockets. There's just everything that you guys can imagine being tested. Materials, structures is getting tested. And MTS will have a piece of equipment to do that. This is kind of a cool thing. This is a driving simulator. There's about 3 of these, the biggest in the world, but this is in Tokyo, in Tokyo City in Japan for Toyota. A car is inside of that, and then there's a motion platform that hang on. So there's a car inside of this, and then it puts a virtual reality inside of it, and a driver is inside this car moving around, and we imitate the motion of a road infinitely. Very difficult to do, but there's a couple of them that are able to do that, and they use it for safety, for dashboard designs, reaction time, things like that. Here's something about in the rail industry. This is a pantograph tester to test how pantographs react. Something that was done by the China Academy of Rail Sciences. This is a bogie test system for a rail train. On the left, you'll see all these force diagrams. They have about 30-some actuators mounted across the bogie, and then we replicate all those forces that come from a testing standard out onto the system. Everything's done in sync with each other, or synchronously. And then they look at that and they use that as test results to see that the bogie frame is behaving as it should be, as it was designed. This is some aerospace testing where there's a full ultimate strength test of a wing. There's a landing gear test system on the right. The bottom left is something to test the aircraft tire system. This is to simulate at the time it was a Boeing 747 landing. So we take all the forces of the aircraft as it lands, as it taxis, as it takes off, all the camber on it, any kind of rotations, yaws on the tire are being simulated as well. Not so good at videos. Material testing is kind of boring to look at, but a lot of tension, compression, rotation. So almost anything that you could ever imagine to be tested for materials there's a system to be able to do it, and to also simulate chambers for temperature and things like that. This is for wind turbines. So we're working on doing that. So they'll string a number of actuators along the wings. These turbines can be 100 meters long on one side, so over 200 meters diameter once on the whole thing. So they're quite long, and we test it out. This is a drivetrain and bearing test system, so we can simulate the torques and the forces on the drivetrain for the system. This is an example of what it looks like in our facility. This is something for the energy people, for the oil and gas people, who's testing of pipes. I go through this kind of fast because time is short. We want to get to seismic stuff. This 250,000 foot-pounds, 350 degree Fahrenheit temperature. This is the wave generators that we have done, something to simulate the sea state. We've done these all over. We don't do this too much anymore. We've kind of started to pull out of this because we had to give up some things to focus on. I put this in there because this was the first job I had as a program manager for the French Navy. I decided to do program managing because I didn't want to travel so much. My family was young. And the first job was this. And the French, they wanted a meeting every month in Paris. Like, my wife wasn't too happy. So every month it was like back and forth for like 3 to 5 days. Anyways, this is a 600 meters long, 8 meters deep, 15 meters wide. And then we create a sea state with this dual flaps, and then they put boats underneath this, and they drive it through the waves that we create. So the waves can be like a meter high on this. This is another big wave generator we just installed a couple of years ago in Netherlands for Deltaris. Those little waves, bigger waves, they're looking at doing tsunami testing. And then this one was the one they did for the government. They had a good sense of humor. We didn't do that. The customer did that. We didn't generate that way. And then we've done some things for entertainment. If you ever go to the Universal Studios, they have a Jurassic Park, and we did the dinosaurs for that system. So we have that. We do consulting, and we have a really good worldwide service support area. So that basically is MTS. But the big thing, we're mechanical, controls, electrical engineers, and our big goal in life is we want to control motions very precisely, motions and forces, as best we can to replicate testing real-world data. That's what we strive to do. So now we go back to earthquake stuff. And at MTS, we do 3 kind of things. We have hybrid simulation, which we're not going to talk about. We have standard seismics tables, where we are, we just make something and they're set for displacement, velocity, acceleration, overturning moment. And they're products for us. We just send them out. And on the bottom, we do custom systems, which is what we do most of. It was the biggest part of it. Everybody has their own desires for testing. So this is some stuff on MTS experience. I go through this really fast. Came from this company in '59, load frames in '62, became MTS in '63, went publicly in '66. Here's an early test system where they would actually this would rotate, and they would put rocks and they would dig in holes to simulate the road, and then it would spin like a record. And we would have transducers that would be looking at it, and based on what the road was doing, we would then simulate the motion of the car. So that was the early testing at that time. First earthquake simulator was in 1968. Oh, that's a good picture of this is our headquarters in Minnesota. This is in Public Works Research Institute in Japan. They have an 8 meter by 8 meter table. This is at E-Defense, which is currently the largest earthquake simulator. There's the happy guys that had done the install work. The nice thing about MTS that we've done is we have gotten to work with some of the most brilliant, passionate researchers in the market for years, for decades, really. And it's been through that kind of collaboration that we have been able to increase our capability. So this is another key message I can say, is that MTS has been successful because we collaborate with customers. So many things we do We don't know how well they will work. No one does. But when you have a good collaborative effort or relationship, good things happen. And so a lot of our business is built on trust, both ways, and it's the best way to work a project going through, I can say. So I know that earlier we had the presentation about the seriousness of earthquakes. It is the #1 cause of death and destruction and financial repercussions in the world, by far. I show some examples on the bottom. The one in China in 2008, in the Sichuan province, killed, I think, about 70,000 people. And the Chinese government decided they needed to get their hand on earthquake technology and designs. So they just started to invest heavily in it. So I would guess that in the last 15 years, probably at least 75% of earthquake systems, testing systems, have probably come out of China. And they're used for bridges, building, various type of equipment. We have tsunami things for wave basins. They look at soil testing, and of course, seismology. There's scaled model testing, component testing, shear walls, fastening systems. A big area has been nuclear power plants, where everything inside the power plant needs to be tested. And those test standards are very high. I will show you something later on about that. But we use the shake tables for shipping simulation, satellite launches. There's multi-table tests for bridges. So you can see the list here. We have like I said, everything that gets made is probably tested. And there's probably a system that MTS has done or can do to help to test that. It's how we've made our business. And our business is probably maybe $400 or $500 million a year of revenue, roughly. Okay, so with earthquake records, and you guys probably already know this, but most of the field data is triaxial, and it's translational, done in terms of X, Y, Z, we would call it, or longitudinal, lateral, and vertical. The testing systems are usually one axis or biaxial. It can be either horizontal, X, Y, or maybe X, Z, longitudinal, vertical, or triaxial. Triaxial is really, if you can do it, this is the best way to go. That saves you the most time in setup and gives you the most realistic testing, would be triaxial. So, one of the things that I hope to come out of this visit today is that we started a conversation about some sort of system here in Indonesia, or maybe multiple systems. But MTS would like to be part of that conversation. And it's the trade-off between what you do for a lab and what you want to test. There's just many trade-offs that have to go into it. Kobe earthquake was very long displacements. Everybody before Kobe in '95, things were tested very short displacements, like maybe plus or minus 125 millimeter. Well, today we're having seismic systems with up to plus or minus 1 meter, something at plus or minus 1.2 meter. So it shifted the whole way of thinking on this. So there's much more higher displacements that need to be tested, and about near fault testing as well. Now Tohoku, which the Fukushima earthquake, was very long in duration, but it was very low in displacement. But it took a lot of power to actually simulate this. The earthquake lasted like 3 minutes. So another thing that has to be thought about when we start a conversation is how big of a system will you have? And then everybody wants a big system, but you can't afford a big system. Very few people can. There's only one in Japan that's like really full-scale system. Then there's some 8x8 systems or 8x10, but those are usually very big investments. And almost all of them will scale the model. So how much scaling is going to be allowed is something that needs to be thought about as well when you're thinking about a system to buy and what to test. So it makes a big difference in terms of one's philosophy about creating a model. Most people want it to be as close to one as possible, but there's trade-offs, always trade-offs, and you have to come to terms about what you're comfortable with. What will the research bear? So there's a couple of scaling methodologies for Cauchy, and there's a Cauchy-Froude method. Cauchy is, by itself, is good for restoring forces, but the acceleration needs to increase, which is expensive. And then the Cauchy-Froude one keeps the acceleration at the same, but then the density of the materials changes, so that you have to then be sure to understand what your material characterizations are. As you study your results, you have to know the results of the type of material that you've done. And there's no unique answer for it, but great care must be taken in the method. And this is, I won't talk about this, but this just shows the different kind of scaling methods and what they do in terms of the different parameters, how they get scaled. In China, we're working on a system where they wanted to test high arch dams. I don't know if any of the dams you have here are high arch dams. I heard a lot of dams, but I'm not sure which ones. I will show you a system that they're working on, that we're working on right now. But one of the people needed it to test high arch dams, which required us to go up to 50 hertz. The system they wanted to run on it was a 16 by 20 meter table that only went to about 20 or 25 hertz. So we needed to get to 50 hertz. And this was the methodology. So the natural frequency of the dam is like 5.56. And then the reduction ratio of frequency required us to increase the overall operating frequency up to 50 hertz. So if you wanted to test that 5.56 hertz, given the scaling, we needed to have a system that could simulate up to 50 hertz. And then you see the different natural frequencies in general for multi-store, granary, soil, or foundation, and it's the same kind of idea. This kind of thing is a good place to start about when looking at what kind of system you want to have. And then on the left-hand column here are a number of different dams that they looked at and how they did their calculations and rationalizing what frequency they could live with. This is at Tongji University in Shanghai, and this is an example of some of the models that they have tested. We call this their graveyard. These are all tested structures that they put on our table. The table we put in was delivered in 1984, and it still runs today. It was a 4 meter by 4 meter table. They upgraded some actuators to a little bit higher performance recently, a few years ago. But in China, they were one of the early people to be studying earthquakes. The other thing is that there are many, many testing standards associated with the different kinds of structures. And of course, we have to support that. We have to be able to ensure that our system can easily work from a recorded earthquake or a shock response spectra or some sort of spectra that's contained in one of these testing standards. So on the right, there is a kind of a hierarchy where you have the national standards, and then you have stuff that's done more locally from departments in the national world, nuclear authorities, and it kind of goes down. But within the testing standards, there are like 4,500 other standards that are referenced. So I guess as a government agency, you guys understand standards and codes and stacks of paper. We have to simplify this to get down to what we can actually use. So again, I won't go in detail on this, but there's codes for nuclear components, there's codes for electrical switch gears, there's codes for non-structural equipment, and different researchers, universities, testing houses specialize in these different kinds of testing standards. Okay, so this is about the fundamentals of a seismic system. I just have a few slides on this. So we understand the purpose is to simulate an earthquake, do qualifications and shock spectra. We look at resistance and of the structures and components, and we verify the analytical models. That's the main goal is really of a test system. The idea is you need to have really high fidelity reproduction to know that your designs are okay. That's where MTS comes in. Our motto is be certain. We want to be certain that what you're looking at, what we're doing is good, that you can bet on it. You can make decisions based on the equipment that we provide. So the best approach to a system design is to try to, this is now getting into our world, is eliminate any kind of reduce the unwanted distortion in the system, anything that's going to cause things that are not related to a test. And the size of the, we try to size the system to fit the work envelope as good as we can for various reasons that enhance performance. We don't want to make something that's too big, because the bigger you get, all errors are based on the size of the equipment, really. It's usually a percent of maximum full scale, which is another thing to keep in mind. The bigger the full scale, the bigger the the bigger the errors will be. It's just the nature of it. So in reality, compromises are made. And you have to be comfortable with that, but it's always going to be compromises. So we ask about what are the main testing requirements, the size of and mass of the specimen, what type of tests are going to be focused on, and then how big of a system. So here's the next big thing. I probably have like 5 big things to talk about, but this is one of them. Actuators are like power regulators, and power is what really drives the price of a system. So it's force times velocity, or mass times acceleration times velocity. So that's what's going to dictate the cost of your system. The bigger the mass, the more acceleration you want to do, the higher velocity you want to do, the actuators get bigger, the servo valves get bigger, the hydraulic power units get bigger, the distribution gets bigger, and prices just sort of go exponentially. So it's part of that thing about compromises. You have to think about what's realizable, and then what do you want to do, what's necessary, how can you scale. So it's a game that you have to play to get to the best solution. An overturning moment, by that we mean when a table or a specimen is on a table and it's rotating around, that motion has to be calculated into our sizing to be able to compensate for when the building is rocking back and forth. The ground isn't really doing that, so we have to be able to make sure that we have that in our ability to compensate. A big part of these systems is the isolation mass or the reaction mass, where you are basically a big piece of very dense reinforced concrete that is used to dampen the vibrations from the table so it doesn't impact the neighboring community. And it's a big part of the cost of the system as well. And it's important because these earthquake simulators will shake buildings. We've had in Japan, they will put these in Tokyo, and it's very dense. And there's places where the neighbors in apartment buildings will call and complain that things are falling out of their cupboards. So the testing will have to be done at only certain times, and so it's another concern that has to be taken into consideration. And then these take a fair amount of electrical power to run. So it's another consideration is how much electrical power can you get to the facility to run a test. So it's another part of the equation about the trade-offs that have to get made. So, general realities, ideally researchers want to do the lowest modeling similitude possible. Larger specimens, which would be for that, requires a larger table and increases the power. Longer stroke requires larger volume actuators and increases the power. Higher frequency means it goes against larger tables, lower the frequency. So when you get to bigger systems, as the systems go up in size, the frequency bandwidth goes down. And that again has to do with the physics of it. So most people want to do low modeling similitude, but they want a big table to do a lot and have high frequency, but they can't get there. And then again, higher accelerations as well, larger areas, which increases the power requirements. So smaller tables, which I would say is like 1 meter by 1 meter up to 3 meter by 3 meter. The capacity is usually 1 to 10 ton, and they can get up to 100 hertz. That's with the displacements probably being around 100 plus or minus 150, maybe plus or minus 200, but you're better off closer to in that plus or minus 150 range. But they can have higher accelerations. And then larger tables, bigger specimen, lower frequency, generally lower the accelerations and longer strokes. Okay, this slide is about the things that MTS faces. This is like going to war with all these things that are causing problems for us to get the highest fidelity. These are competing system dynamics. The specimen resonates, has the overturning moment. The earthquakes require operation over a wide frequency range, so it's difficult to have good error, low errors over wider frequency range. If you can focus in on a frequency, you can do better, but this has to cover a broad frequency range. The table itself resonates. The actuators are very dynamic. There's something called oil calm, which is the springiness of the oil. There's cross-coupling between the actuators. I do something here, I'm going to feel it over here. So you have a motion in, but it's going to be felt in a different place. The actuators themselves have natural frequencies, so they can start to absorb energy. And what you think is going into the table and the specimen is only going into the actuator. There's friction. There's servo valve limitations. There's swivels themselves that have limitation. Hydraulic flow has its own characteristics. And the foundation itself has only so much stiffness. So what MTS does, we try to think about these things, and we have, over the years, have come up with techniques to minimize these defects. Those things will show up in your testing. So we show here what the actuator bowstring, what frequency it might show on, the oil calm, the table resonances. This is showing a bare table, and then with a specimen, how things shift around on that, depending on what you're running. So these are real disturbances that will impact the results. They show up. So they need to be identified and addressed and minimized as much as possible. Okay, and this is what a seismic system basically consists of. You get the table. You have a reaction mass that holds the table. You have actuators that connect from the reaction mass to the table. There's a controller and data acquisition. And then you have a hydraulic power system, which is usually a bunch of hydraulic power units. They give you a constant flow. And then you have accumulator banks, which is a better way to store energy without having to use hydraulic power units. So we fill accumulators up with oil. I'm going to use PSI, generally to 5,000 PSI. And then we lease that, and we operate at 3,000 PSI. where we store up 5,000 PSI, and then we regulate it out into the system as we need it at the operating pressure of 3,000. So the reason this is nice is because sometimes electrical power is a problem, and it costs money. So we find that you can compensate for not having power units by having accumulator banks. So it's a trade-off again. Hydraulic power units will give you constant flow. You know it's going to be there. Accumulator banks charge up, and then they will dissipate. And so they're going to limit the duration that you can run when you need to have high peak flows for the system. Again, it's a trade-off. Okay, so now I will show you some standard tables, and then we'll get to custom tables. So this is a uniaxial 1.5 meter table. Here's a uniaxial 3 meter table. We have a stanchion, an actuator, and it's on a system, a bearing system that moves it. There's a biaxial system that has another actuator in the perpendicular to where that actuator is set there, so you have the XY motion. Here's the kind of performance for those simulators. So these are easy to make for us, and designs are done. It's lower cost sort of thing. Quick video here, just kind of showing what this looks like in the lab. Then this gives an idea about the approximate footprint of this, where it's an 8 meter by 8 meter by about 2 meter deep. This shows an example, a nice cross section of the foundation, where you have, here we have the, embedded into the reaction mass, we have subplates, and then we use a big tie rod. So the subplates are at the bottom, and then a tie rod comes up, and we put the mounting plate for the actuators there, and then we compress this, and then we have a very good tight tie of the actuator into the reaction mass. So we do that for all the actuators. This is a site, a couple pictures are showing how this was installed. This is in Chennai, India. I think I said that right, Chennai? At IIT Madras, I believe. These are MAST systems, M-A-S-T, multi-axial simulation tables. These are also standard, a product that we have. And there's, this one is getting used more and more by earthquakes researchers. This has a 2-ton capacity, can go up to 100 hertz, and then you see the acceleration there, which is pretty high. And the velocity is pretty good, and then you have the lower frequency, which allows the higher frequency performance. I'm sorry, the lower displacements, which give you the higher frequency. But we have a whole set of these kind of mass systems, so there's different options to choose from. But basically, it looks like this, where we have the mass, which uses that actuator configuration. It's called a Stewart platform. And it just hooks up to a pump, a manifold, our controller, and it's ready to go. Here's an example of some components in a typical lab configuration, where you'll have a mast system on the right, and then some structural actuators out on the left-hand side for doing different kinds of testing. A controller for the structurals, actuators, a controller for the mast system. This is an example from a lab in the US in the state of Nevada called Dynamic Certification Lab. And they focus on non-structural testing for the AC 156 standard. It turns out that I think 85% of the financial damage from earthquakes, 65 to 70% of it, comes from non-structural components. In the state of California, all non-structural components that go into any kind of government facility or one that's deemed necessary, like hospitals, have have to be tested for the AC 156. And they will send it to a company like this to make sure that these that they run, or the suppliers of the equipment will run it, send it to these places. So here's kind of what the documentation looks like. This is an air handling unit. So I won't go into the details here, but they have a performance envelope that it needs to meet. And they want to make sure that you're outside of that envelope, nothing underneath it when you run your test. And it all has to be certified and stamped and in order to be approved for being used. So as you can see here, this is the table. Since this air handling unit is a little bit bigger than the table, the 2.2 meter table, there's an extender that allows for a bigger specimen to be put onto it. Here's a control panel getting tested on it. Again, these mass systems have a purpose, and they're not that, well, relatively not that expensive. They're designed, ready to go, proven out, big in structural, big in ground vehicles, so we have a lot of understanding. I think we've sold of that, all of these mass, over 200 of them are in the field. This is a 4 meter by 4 meter system. Now it starts to get more interesting in terms of bigger structural testing. So you got the table, the foundation. In this case, it's 2 or 3 hydraulic power units, 1, 2, or 3 accumulator banks in the control room. So the basic setup looks like that. Or the layout there, schematic. We've designed this for a bunch of different capacities, a base system, something that's longer stroke, higher velocity, higher force, something with higher force and velocity. And we can kind of mix match these actuators. So again, it's a case where we have proven ready to go designs and to try to help keep costs down. The performance curves for it, which we won't talk about right now. This is just some examples of what's involved in it. I'm going to go fast because there's more that we really want to get to here. This is what the table looks like with actuators. Kind of what the hydraulic power system looks like with the pumps, accumulators, a reservoir, and then out to the actuator area. These are the accumulator banks we talked about already, where the 5,000 PSI charge goes into. Pumps, the cooling system, usually not supplied by MTS, but it's supplied by the facility contractor, something to cool the oil. The control system, which we'll talk more about this afternoon. We have data acquisition that can be hooked up to the test specimen as well and integrates in with our system feedback. And then I have some layouts for that as well. For this 4 meter by 4 meter, the moving mass, which is the specimen, the table, the attached mass, which is actuators. And then what you end up using is usually shooting for something. It can be from 20 to 1 to 50 to 1 usually, depending upon what kind of reaction mass you have. This is a fixed reaction mass, but there's also a suspended, or we call it floating reaction mass, which they use in Japan quite a bit, and in Taiwan, where there'll be air springs underneath that reaction mass. So that helps to dissipate the vibrations. So underneath there'll be a set of air springs. I think this is like a 14 meter by 14 meter kind of area, maybe 6.5 meters deep. Here's a better picture of the tie rods and the mounting plates. And again, that's not supplied by MTS. Usually the customer is responsible for the facility, foundation design. We can provide the layout and where all of our equipment's going to be. They'll take care of embedding the actuator mounting plates, power and hookup, and the cooling unit and crane. Usually comes from the customer side of it, not in MTS's scope. Just to give you an idea on that, for that 4x4 system, the reaction mass in the US On a cubic meter, it's more like probably $700, $800 per cubic meter. And in Mexico, a few years ago, it was more like 300 per cubic meter. And we know in Asia, it's sometimes somewhere in this $450 per cubic meter kind of price. I'm curious what it would be in Indonesia. Maybe you guys know, but I'm guessing something like this. That embedded hardware is probably about $50,000. And the cooling system for that system, which had 2 or 3 HPUs, is in the $300,000 to $400,000 kind of price. So these are significant costs, and they have to be part of the overall system budget for sure. Okay, custom tables. And I'm going to do this really quickly here. This is the largest system in University of California, San Diego, largest outdoor system, a 7.6 by 12 meter system. And they can do tall buildings on this. This has the largest specimen capacity at 2,000 ton. This is the largest in the world for a specimen that can be mounted on top of it in terms of mass. They did a 6 degree of freedom upgrade. It was uniaxial in like 2003 or 4. And in 2019, I think, was when we signed a contract to make it a 6 degree of freedom system. So now it's 6 degree of freedom. Here's an example of some videos of the different kind of testing they do on it here. Shear wall stuff. For the sake of time, I'm not going to show many of these right here. I'm going to kind of move fast because you can find these kind of stuff on YouTube and find different kinds of testing that they've done on it. But they've done a lot of testing. Really good research team at the University of California, San Diego. This is now in 6 degrees of freedom of motion for that table. The Boss earthquake. This is in San Diego, which is, the temperature is usually really nice, not too much rain. Although they did just have a hurricane. Two-story prototype. I like showing this one because of the isolation bearings. So guess which one has isolation bearings? One on the left. Or, I'm sorry, the one on the right. Okay, 6 meter by 6 meter examples. We also have one in Chongqing. This is an underwater system. We've done 3 of these. This is a system in Kyoto in Japan. This is at Busan National University in South Korea. They have 3 tables. This is at Tongji University, where they have 4 tables that can be repositioned along these trenches to do this different kind of testing that you see here. Along bridge, building, a stadium, and the one on the upper right is a train. They put the table in these different orientations for testing. These are biaxial tables that are currently being upgraded to triaxial right now. See that big strong wall right next to it? They mount actuators on that and then can press against a specimen while a shake table is running. So they get testing coming from 2 different places. Here's an electrical component manufacturer in Suzhou, China. They have 2 4x4 tables. And on the right is when they're joined together to make one larger table. I won't talk about that. This is used for component testing for nuclear power plants. As you can see, this one has 6-ton capacity up to 7 Gs. And it's used for testing the AP1000 equipment, which is the Westinghouse nuclear power plant design. And the Chinese have the similar thing called the CAP1000. This is a system also at the Busan for doing nuclear power plant testing. As you know, Korea is putting out, providing nuclear power plants, especially in the Middle East right now. And this one has had similar kind of performance on it. This is at the University of Nevada, Reno. They have 4 tables testing a bridge. They have structural actuators at the end of the bridge that give the bridge abutment test. This is a system where they hooked up 4 tables and wanted to test the Northridge earthquake against a bridge. Public Works Research Institute in Japan we talked about. Let's go through this really fast. That's the hydraulic power units. Those are the accumulators. These are hoses from the reaction mast to the facility floor. It's a floating foundation. This table weighs about 100 ton. And they can put a 300-ton specimen on top of it. This is at a construction company called Kajima in Japan. They have 2 tables. One is 5 by 7. The other one is 2 meter by 2 meter, which is for low frequency. And they can put the lower frequency test on top of the other table. This is what the distribution system looks like for that. There, on the right, you see that guy. He's about 1.8 meter, maybe. And that's the vertical actuator, to give you an idea about the size of the actuators. Here's that little table moving. It's like a 2 hertz sort of system. This is another construction company in Japan called Shimizu. This is the pump room. HPUs on the left, accumulators back on the right, of the hard line running out to the system. This is I'll show you the test specimen that they had for this system. Quite a clever design. This is from a news company over there. That's what they gave as their test specimen for acceptance. Japan's really advanced in their research with earthquakes. You guys pulled out. Understand or no? This is the biggest system in the world at e-defense. They have, I think they have 24 actuators. Each of the horizontal actuators have 3 10,000 liter per minute servo valves. So each horizontal actuator is getting 30,000 liters per minute. And there's 10 of them, so there's 300,000 liters per minute of oil going to just the horizontal actuators to give you the idea about the required hydraulic power for the system. This is a system at Southwest Xiaotang at the Shenzhou. This is in Chengdu. 8 meter by 10 meter table, and then a repositionable 3 by 6 meter table. Here's got plus or minus 800 for displacement, horizontally 400 vertically. I have to be done by about noon, so I'm going to really go fast here because I want to show you some of the stuff on applications. The table here, 105 ton, done in 3 pieces and then welded and bolted together on site. This is that Encre. Isaac knows this system really well. It has a bearing, isolation bearing test system up in the upper left there. And then they have a strong wall in the middle and then an 8 meter by 8 meter table off to the right. So Encre is just really world-class researchers. The work that comes out of their lab is fantastic. This is plus or minus a meter in displacement for the system, for the 8 meter by 8 meter table. 400 vertically. There's the isolation bearing system, biaxial bearing system. They call it BATS. Prime Minister came and got a demo. And this is for their grand opening. Take a quick look at this. This has 60 meganewton of vertical force. At in Guangzhou, they have 2 4x4 tables and an 8x10 table. The lab looks like. Down on the bottom there, you see another strong wall. So this now is something we're working on right now, and it's really special. This is the biggest system, will be the biggest system in the world. This is for Tianjin University. It's called the National Facility for Earthquake Engineering. Started in 2017, and we think what we get done in 2024. So I go through a little bit fast. This is the lab that they want to have. The comparison here to e-defense. Similar displacements, more velocity in Japan, but more acceleration in China, and more specimen capacity in China, 1,350 ton versus 1,200 ton. Won't talk about this. This is what the layout looks like. On the left side, you have 2 6 meter by 6 meter tables that can support 150 meter ton apiece for bridges under 3 meters of water. And then they have a wave generator system that creates a sea state, 91 channels, and they use it to test bridges, piers, whatever. And on the right side is the 16 meter by 20 table. That gives you an idea, a better idea what that facility looks like. Here's the 16 by 20. So they have, starting up at the top there, we have the reservoirs that feed oil from some transfer pumps over to the filters and the cooling system, then into the HPUs. HPUs will send it out to the accumulators. There are 72 1,600 liter accumulator banks, like 115,000 liters of volume for accumulators. And then they have 10 2,800 liter per minute HPUs. So that's just to run this table. I'll give you an idea of what that distribution system looks like. And there's the picture of the table, and you can see the people at the bottom there. I'll give you an idea about the scaling here. This table weighs 800 ton. And here's the 6x6 layout. There's a water seal that goes around the table, so no water should go underneath the tables. This is the thing we talked about earlier about the scaling that they did. So this is the table that we put on top of it. It's an 8 meter by 10 meter table that will sit on top of the 16 by 20 table and gets them up to that lets them put a dam on top of it and gets them up to 50 hertz. And both tables can run at the same time. So the table underneath can run at up to like 20 hertz, and then the table on top can run from 0.1 hertz up to 50 hertz, or we can frequency switch and let the higher frequency stuff happen only on the top table. And that's what this system looks like. There's a big reaction frame there used to, for the actuator reaction. It's kind of the technology that's used for it. A pretty elaborate control system across these different systems, all interconnected to each other. And then here's some installation photos. This is the dream. This is where it was in 2021. Here's some installation construction photos. Give you an idea about the amount of rebar. This is the area for the actuators for the 16 by 20 table on the right. And then on the left is a good view of what it looks like for the 16 by 20 and the other tables. They have two 500-ton cranes. This is all MTS design, by the way. And we work with a local manufacturer for the hydraulic power units and the few parts of the equipment. This is in MTS's factory, kind of a quick shot here about what it's like to make these manufacturers. So we planned it out really well about getting from one end to the other end. So closest to us is for assembly, then it goes to pressure testing, then a place for checkout for its more rigorous testing. Hello? Okay. I think that'll be better. Here's the 6x6 installation photos. This is spring this year. Here's the frame for the seal. And here's a couple weeks ago. This is from a couple weeks ago, where we have lateral, longitudinal, and vertical motion, and the lower left is a more random wave. And then these are for the big system, the vertical actuators. They weigh 23 ton. They're about 6 meters long when extended. The pit area here. We don't have time for it, but here's what it looks like when they're all installed. So 18 of them in there. And here's the horizontals that we have. These weigh 12.7 ton and are about 5.6 meters fully extended. And we have 8 more to install for this big table. And then we will install the table. And we should hope to have everything installed by the end of this year. And here's something about the table. This is the guy that runs this the project over there from Tianjin University. So it comes in 6 pieces, and then they get, like I said, will be welded and bolted together. And this will be final machined on site. So they bring a CNC machine to the facility and finish the machining off then. This is the team from MTS that did the design and manufacturing. And this is the MTS China team. And so that, and I have 10 minutes, and I was going to try to show you some examples of some applications. So I'll do that quickly so we can have lunch. Oops. So this is in Guatemala, and they had they wanted to be able to better understand some of their heritage buildings that they had, to understand how earthquakes were affecting them, and then also be able to fix them and then to support them so that they don't get damaged. So this presentation, and there's a paper that's referenced as well, discusses that. So I'm going to kind of go through a little bit fast. You know, they're subject to earthquakes in Guatemala. Earthquakes are bad. This is the earthquake that they were interested in. Then it goes into how to model the church, our system that we put into it, then the scaling that they did, how they adjusted the earthquake time history to test it, the techniques and the skill involved in building the model. These guys are almost like artisans when they do this work. It's really great. Then they instrument it. They have their mathematical model, and they're going to try to validate that model. The end story is that it was they did a pretty good job modeling. And then here we have some examples of the test. This was done on a 3 meter by 3 meter biaxial table. And this one, they wanted to break it. Come on. So then they study where all the cracks were and where the faults were. So that's one application use that was interesting and maybe some ideas for you. Here's another one I think that you'll be interested in. I heard about wood buildings earlier today. Purpose of the test, the researcher's overview. So in the US, a lot of funding for earthquakes come from the National Science Foundation and the Department of Energy. And they formed this big group, have been working on it for probably 10 years to study wood building, wood structures. And so they wanted to build a full-scale test for a 10-story cross-laminated building. So in this chart, it just shows you the flow and their mental process on how they got to the final designs. So done in a scientific method, for sure. And here's the team that worked on it, multi-universities. Those are the principals there. Here's collaborators. A lot of people from industry were involved in it. And here's a view of the design. We don't have time to talk about this, and frankly, I'm not a civil engineer. You guys would understand this a lot more. And you can reference the paper for this. But it has a lot of the details. This is well documented because it's the government. There's a website you can go and find a lot of things, which is where I took a lot of this information from. This shows where they've got the columns and the what the grid structure of that looks like, and where they have the walls. this year. They don't have any results yet printed. I tried to get some results, but they're still compiling them and they haven't released them yet. The big red thing there is to protect the control building, which is the building on the left, which is where all the hydraulic power units and the control room is. So they put that red structure there as something that would hopefully protect it in case it tips over. But when they run the test, the operators don't go in that building. They're way away from the system. So amazingly, we got to noon. And that was about it. So I apologize if it was fast, but this is a really exciting work that we do, and we really hope and look forward to being able to work with you. Something here maybe is interesting, and MTS would love to be a partner with you. And we're there in any capacity to answer questions, to collaborate on a proposal, to, I think a lot of times you have to get people together to come up with what do you really want. These jobs, the bigger jobs, take many years to put together. It's collaboration internally with your research community, and it's coming to a supplier to figure out what can be done for what price, iterating on it, then selling higher management within the government. And we really understand that it takes a long time to come up with the funding required to build something like this. But they last for 30 years. So you want to do it right when you do it. So anyways, thank you.
Okay, we give applause to Tim. Thank you, Tim, for the great presentation. I think it's better if we have a question now.
Oh, good.
Give maybe about 10 to 15 minutes before we break. The floor here and also online. If you have any question. Ya, mungkin untuk Bapak Ibu, untuk MTS ini mungkin kalau kita bandingkan seperti mobil, MTS ini mungkin seperti BMW atau Mercedes ya. Jadi MTS ini punya histori yang panjang di dalam alat-alat pengujian, terutama pengujian dinamik, shaking table atau aktuator. Saya pikir seperti yang tadi sudah disampaikan, banyak lab-lab yang kelas dunia itu menggunakan MTS. Ada pertanyaan? Bapak Ibu di sini mungkin yang rencana untuk mau buat lab.
Okay.
So I would like to ask something. So do you have any experience regarding the LRB test? So as you know that the currently we have only two fabric. I think that you use LRB test in Magdatama and also in Bukaka. But in terms of the government, we don't have that yet for the dynamic test for LRB. So do you have any, what is it called, the typical one for LRB, for bridge, and also for probably for building, I think?
No, we don't. The thing about isolation bearings that make them challenging, there's many different systems out there. Some are static, which is just really very slow, not so realistic. And then there's more dynamic ones. Of the dynamic ones, there's probably 4 of them in the world of bigger capacity. 2 of them are in Taiwan. Then there's one at the University of California, San Diego, SRMD it's called, and there's one in Italy. And MTS has done those, but they're all fairly unique. The stuff out of Taiwan is kind of interesting because it's a good design and it could be useful. So we would probably try to leverage that as much as possible depending on what the requirements were. But the thing with isolation bearings, remember when I said it was about power? So with seismic, force and velocity are usually out of phase. With isolation bearings, they're in phase. So you need the most hydraulic power for those. So everybody wants to get an isolation bearing test system until they hear how much oil it will take to really do a test. So, so not many people can afford it, really. It's a big government sort of thing, generally, that has to be done because of the power requirements for it. So we have actuators that could be used. Some people try to do, in Japan, I think they just put together something, but they bought actuators, and somebody from the Japanese National Institute or National University had their own kind of design, that kind of thing. But no, sorry.
Okay, Tim, we have another question from online. This is from Mr. Aryono Danis. What literature or book to describe how to do scale down of the rail bridge to the laboratory bridge to test on the shaking table, or any code how to choose the scale?
Was that a book reference?
Yes.
Yeah.
He asked for the book or reference or journal how to make a scale
Yeah.
for the model.
It's a really good question. So we have to pay attention to that, but we are not experts in it, really. But we've had to come to appreciate it and understand it more recently. And it was hard to find something concise that would do it. So we've done some searches for it. And I can't reference a book right now, but I have like maybe 4 different presentations that I found that are pretty good and give a good explanation about it. And I will provide those links and those papers. I will get them to Tamara, and then they can put them up someplace publicly where people can grab them. And it'll be helpful, I think. And then there'll be acknowledgments and references, and people can go down that, that rabbit hole of modeling.
Okay, thank you. It's great if you can give us some journal or books.
I will do that for sure.
Another question. This is from Mr. Rido Satkar Pepe Sumbar. In Indonesia, since 2009 earthquake, especially in West Sumatra province, in 2010, the escape building, the government's office, and the West Sumatra Provincial Public Works Department have used seismic-based isolation foundation, but using this requires very expensive maintenance costs. Can this system save more on maintenance costs?
I didn't follow that really well. So I was following it where they have foundation isolation for the building, but then it was about maintenance.
Asking about maintenance costs, or maybe you have experience about this.
I don't have anything on the isolation bearing maintenance. Do you have anything, Isaac? Or
So for the maintenance on the isolation bearings, the rubbers inside the isolation bearings will deteriorate throughout time. So normally we expect it has its life expectancy on 30 to 50 years. Depends on how big it is and what kind of structures or buildings it's in. And sometimes we design that it can be replaced one by one. So you don't have to replace it all in one time. You can just replace like 20% of them in 5 years and 20% of them in next 5 years and so and so. So from my experience that we have the isolation bearings installed in the building in Taiwan, then they would like to have more and more small scales isolation bearings instead of one big ones or few big ones to just save the maintenance cost and replacement cost. But I will say that for the government building or for the schools, we want to design these buildings that it will not collapse after the big earthquake. It will be damaged, it can be repaired, but it just will not collapse. So on cost-effective ways that I think it still needs a lot of progress on the isolation bearings to just reduce their cost and maintenance works, and then it can be applied to like government or other like infrastructures all over the world, all over the country. But right now we can see more and more applications on it, and like bridges and nuclear power plants. These are the main focus that we install these isolation bearings at the first priority.
Oke, thank you. Ada pertanyaan lagi dari floor yang hadir di sini? Okay. I have a question. I have seen that you also produce an actuator, or the dynamic actuator.
Yep.
And can we use...
Or static.
Yeah. Can we use this actuator also for the shaking table? So if we have a table, and then we have an actuator, a dynamic actuator, and if we put this actuator on the table, is it possible?
Oh, sure. Yeah. You have to be careful, of course. You have to make sure that wherever your actuator is capable of, the table can't move beyond what it's going to take the actuator in terms of swivel angles, or you'll start to damage things. The other thing is on actuators, there is a cushion built into the end caps. And this cushion is designed to meet an appropriate mass and velocity, worst case. So this is the idea that it's the safety valve, safety function of the actuator. So the rod that moves back and forth has a mass, and then whatever it is you're moving has a mass. And so the cushion for an actuator is designed for something, right? And if you just take a structural actuator that has some sort of dynamic capability and say, oh, I'm going to use it over here, you have to take care that what over here is about isn't going to exceed the capacity of the cushions within the actuator. Because if you do, it's a bad thing. The actuator can explode. The end caps break off, and it's not what your lawyers would like to hear.
But
if you check, you can.
In principle, you can design a system like that.
Yeah. What I was going to answer, you make me think about another comment about the isolation bearing and a seismic table. So once customers have a seismic table, they have all that hydraulic power there, they have a table, and it's like, I want to do damper testing, or I want to test isolation bearings. So if you think about the table is here, and then you have the facility floor or a strong floor here, customers will mount an actuator here, and they will put the table here, and they will use this as a way of, and then they'll mount this isolation bearing, and then they will push it back and forth like this, and they'll do that for dampers, and they can also come up with a reaction mass for the vertical forces for the isolation bearing. So it's not purposeful for that thing, but there's ways of taking advantage of what you have to be able to do more tests. So, and the same idea for what you're discussing as well, how to use a structural actuator for more testing.
Thank you. I have another question from online. Question to Mr. Tim. Indonesia is one of the countries that is in the ring of fire. What is the handling and prevention of earthquake and tsunami in a cheap and effective way, considering that Indonesia is very large and the disasters are complex?
I didn't quite understand.
Exactly.
Yeah. So the question is basically, do we have experience with multi-hazard testing? Yeah. This is another good question, and it's a good one about where a lot of research is going to, especially in the U.S., I know, I imagine other places as well. And some facilities are, money is easier to be found now for hazard research and development, where seismic was the big thing in the 90s and 2000s in the U.S. And then just maybe in 2012, 15, somewhere in there, the funding started to switch over for the multi-hazard and the fires, temperature, tsunamis, and things like that. So we have stuff in the tsunamis test, but and we have a lot of things that work under fire conditions. So let's see, I'm reading the question. Oh, okay. Yeah. I don't have a good answer about what's a good way to handle that. I only know about testing, and I think that Mother Nature wins all the time.
Okay, so for the multi-hazard test in right now, I think it's like a trend to worldwide researchers. We do have a cooperation lab in New Zealand, which will test the fire hazard on the concrete material. After that, they just set a big fires on the concrete material, and after that, they move that material to structure testing lab to test the properties before and after the fire. And I think the first things on these kind of research is on material-wise. So you just don't test the whole structures with these kind of multi-hazard, because the hazards will come, and it could be really large, like tsunamis. When we have the big tsunamis on 2004, the earthquake on 2004, the tsunami is so big that you cannot prevent, and you cannot make the right testing conditions out of that. So the first thing is that we study the materials and the scale down models, and then we're starting to improve our research on that. And also right now we are using more and more computational models. And of course the multi-hazards computational models can combine with computational fluid dynamics with the structural modeling. So that's what helping us understand what kind of tests that we need to do on the real world. And after that, you can define what kind of tests you would like to do in your laboratory and what kind of results and you want to get from these tests.
Okay, thank you. Is there any question here? Okay then. here we have another question. If I'm not mistaken, the Indonesia has produced the LRB question. LRB is deemed as biaxial and triaxial, and how could we assume that the dimension? I think the question is not suitable for this. So I think
there's been a lot of research on LRB bearings. So I would guess, I don't know, I would guess that no one's guessing about it. It's pretty well engineered, and a lot of tests have been run on LRB. So I don't know that question is. How could we assume the dimension of LRB if there is no research on that? I would say that there is.
Okay. I think we enough for this session, and thank you, Tim and Isaac, for the answer.
Thank you. Thanks for your attention.
And we give applause to Tim. Okay, we have lunch until 1 o'clock, and we back again at 1 o'clock. Thank you.
Okay, thank you so much. We have to break until 13, and for all of the speakers to have a meal first, and then the next is for the participants. We invite all of the speakers to lunch first, and then the next is the participants. Untuk bapak-bapak, ibu-ibu, ini setelah ini akan dilanjutkan lagi dengan sesi panel diskusi, sesi tanya jawab. Jadi kami mohon kesediaannya untuk kembali ke venue pada pukul 13.00 waktu Indonesia Barat. Kami persilahkan kalau yang mau sholat terlebih dahulu, kami persilahkan. Nanti setelah seluruh narasumber kita selesai makan siang, baru kami lanjutkan dengan para peserta secara bergilir ya. Terima kasih. Sembari bapak-bapak, ibu-ibu ini menyantap hidangan untuk makan siang, kami informasikan bahwa acara seminar ini sudah kami link dan dengan Lembaga Pengembangan Jasa Konstruksi LPJK, sehingga bagi peserta baik offline maupun online yang mempunyai sertifikat kompetensi kerja atau SKK bisa mendapatkan nilai SKPK sebesar 5 poin dengan mengisi link yang sudah panitia siapkan. Sekali lagi kami informasikan bahwa acara seminar ini sudah kami link dengan Lembaga Pengembangan Jasa Konstruksi LPJK, sehingga bagi peserta baik yang hadir secara offline maupun online yang mempunyai sertifikat kompetensi kerja atau SKK bisa mendapatkan nilai SKPK sebesar 5 poin dengan mengisi link yang sudah kami siapkan. Jadi jangan lupa untuk mengisi link, ini berlaku untuk seluruh peserta yang hadir baik online maupun offline. Terima kasih. Tempati tempat duduk yang sudah kami sediakan. Sebentar lagi acara akan kami mulai. Acara selanjutnya yaitu melanjutkan panel diskusi berkaitan dengan tantangan Insinyur terhadap perkembangan rekayasa kegempaan untuk minimalisasi kerugian kegagalan bangunan. Nanti akan juga dilanjutkan sesi tanya jawab. Baik, langsung saja kami turut mengundang